institution, Universitas Negeri Malang views education as a universal right that must be accessible to all individuals, regardless of social, academic, or geographical background. As part of this commitment, Universitas Negeri Malang continuously strives to improve campus accessibility by providing Universitas Negeri Malang views education and developing as a universal right student learning accessible to all individuals, regardless of social. Universitas Negeri Malang has also collaborated with many companies in providing educational services, offering various scholarship programs that cover different levels of need and talent. Experienced by every student and is continuously developed to support the entire educational process in each faculty. Faculty of Education. As the oldest faculty at Universitas Negeri Malang, the Faculty of Education has 6 departments that are ready to produce professional teachers in their fields. Faculty of Social Science or sets the standard in learning, research and communication services, both nationally and internationally. Faculty of Letters. The Faculty of Letters has 5 departments that will produce graduates who are experts in both language and Universitas Negeri Malang continuously strives to improve. Faculty of Mathematics and Science has 4 departments consisting of 10 undergraduate study programs, 8 master's study programs, and 4 doctoral study programs. Faculty of Economics and Businesses. Having 3 departments, the Faculty of Economics and Businesses strongly emphasizes quality education and training, innovative research, quality publications, and a synergistic learning system. Faculty of Engineering. Focusing on the study of technological advancements in campus accessibility engineering by providing and application facilities education as a universal facilitates student learning accessible to all levels and professional experts. Faculty of Sports Science. As the only sports faculty in the city, it has a mission to lead in providing higher education services by opening 4 departments that will develop knowledge and technology in the field of health and sports education. Faculty of Psychology is a faculty that has 2 study programs, bachelor's degree in psychology and master's degree in educational psychology. Faculty of Medicine. The Faculty of Medicine offers programs in medicine, nursing, and midwifery. In a warm environment, students are introduced to various aspects of medical education. Faculty of Vocational. Universitas Negeri Malang has also to maximize the development and service of vocational learning, producing applied bachelors. School of Postgraduate Studies. The School of Postgraduate Studies at Universitas Negeri Malang offers opportunities for students to develop knowledge and skills in various fields of education. As a result of these commitments, Universitas Negeri Malang has earned the title of Best University, achieving the first rank in the ICMIA institutions rankings for education field in Indonesia. By continuing this commitment, Universitas Negeri Malang hopes to create inclusive and equitable education for all and become an agent of change that empowers individuals from diverse backgrounds to reach their full potential. Universitas Negeri Malang has demonstrated a strong awareness of the importance of environmental sustainability. With a determination to reduce its environmental footprint, UM adopts various environmentally friendly practices with many companies in providing educational services. Actively organizes environmental awareness programs for students and the surrounding community, enhancing understanding of the importance of environmental preservation and motivating real action. Because UM will continue to be a place where ideas are discovered and implemented to create positive change in local and global communities. UM
excellent in learning innovation.
Offering various scholarship programs that cover different levels of need and talent.
The Indonesian Magnetic
Be
Society
experienced by every student.
is a professional organization dedicated to advancing magnetism and magnetic materials in Indonesia. Rooted in the historic Magnetic Club conferences from 1999 to 2015, IMS was officially established in 2018 to continue and expand this legacy. Today, IMS serves as a growing hub connecting researchers, engineers, industry professionals, and government institutions. At IMS, we connect, develop, and innovate. We bridge research, innovation, and real-world applications by fostering collaboration across academia, industry, and government. We believe that progress begins with shared ideas and strong partnerships. And we are also committed to empowering the next generation through education, training, and mentorship, supporting young scientists and engineers to become future leaders. At the global level, IMS actively builds international collaborations, creating opportunities for Indonesian talent to contribute to cutting-edge research and the global magnetic community. Our work is driven by 4 key pillars: scientific meetings, research dissemination, education, and support for energy magnetics development, powering technologies such as electric vehicles, generators, and sustainable energy systems. IMS is more than an organization. It is a platform for connection, a center for development, and a force for innovation. Indonesian Magnetic Society, advancing magnetism for Indonesia and for the world. Let's join us.
And is continuously developed to support the entire educational process in each faculty. Faculty of Education. As the oldest faculty at Universitas Negeri Malang, the Faculty of Education has 6 departments that are ready to produce professional teachers in their fields. Faculty of Social Science, or sets the standard in learning, research, and communication services, both nationally and internationally. Faculty of Letters. The Faculty of Letters has 5 departments that will produce graduates who are experts in both language and Universitas Negeri Malang continuously strives to improve. Faculty of Mathematics and Science has 4 departments consisting of 10 undergraduate study programs, 8 master's study programs, and 4 doctoral study programs.
Faculty of Economics and Businesses. Having 3 departments, the Faculty of Economics and Businesses strongly emphasizes quality education and training, innovative research, quality publications, and a synergistic learning system.
Faculty of Engineering, focusing on the study of technological advancements in the field of engineering by providing Universitas Negeri Malang education as a universal facilitator student learning accessible to all levels and professional experts. Faculty of Sports Science. As the only sports faculty in the city, it has a mission to lead in providing higher education services by opening 4 departments that will develop knowledge and technology in the field of health and sports education. Faculty of Psychology is a faculty that has 2 study programs, bachelor's degree in psychology and master's degree in educational psychology. Faculty of Medicine. The Faculty of Medicine offers programs in medicine, nursing, and midwifery. In a warm environment, students are introduced to various aspects of medical education. Faculty of Vocational. Universitas Negeri Malang has also maximized the development and service of vocational learning, producing applied bachelors. School of Postgraduate Studies. The School of Postgraduate Studies at Universitas Negeri Malang offers opportunities for students to develop knowledge and skills in various fields of education. As a result of these commitments, Universitas Negeri Malang has earned the title of Best University, achieving the first rank in the ICMIA institutions rankings for education field in Indonesia. By continuing this commitment, Universitas Negeri Malang hopes to create inclusive and equitable education for all and become an agent of change that empowers individuals from diverse backgrounds to reach their full potential. Universitas Negeri Malang has demonstrated a strong awareness of the importance of environmental sustainability. With a determination to reduce its environmental footprint, UM adopts various environmentally friendly practices in companies in providing innovation certificates. Because UM will continue to be a place
Assalamualaikum warahmatullahi wabarakatuh.
positive change in local and global communities.
Good morning, distinguished keynote speakers and invited guests. The Honorable Rector of Universitas Negeri Malang, which on this occasion is represented by Vice Rector 1, Professor Dr. Ibrahim Bafadel, MPD, along with the distinguished members of the University Board of Universitas Negeri Malang, the President of Indonesian Magnetic Society, Professor Dr. Agustinus Agung Nugroho, the Chairman of the 4th International Conference on Magnetism and its Application, Professor Ahmad Taufik, the Honorable Keynote Speakers, Professor Cheng Hao Chuang from Tamkang University, Taiwan, Dr. Mi Jinjin from Institute of Basic Science, South Korea, Professor Koji Nakamura from Mie University, Japan, Professor Markus Tiantoro from Universitas Negeri Malang, Indonesia, Professor Masaki Fujita from Tohoku University, Japan, Professor Warawat Mifasana from Suraneri University of Technology, Thailand, Professor Madhya TS, Dr. Muhammad Safwan Abdul Aziz from University Technology Malaysia, respected invited speakers, professors, researchers, academicians, participants, and distinguished guests. Ladies and gentlemen, on behalf of the organizing committee, it is my great pleasure to welcome you all to the 4th International Conference on Magnetism and its Applications 2026. Ladies and gentlemen, ICMIA 2026 serves as an international scientific forum that brings together researchers, scientists, academicians, and practitioners to exchange knowledge, discuss recent developments, and strengthen collaboration in the field of magnetism and its application. We are also proud to share that this conference is supported by the Equity Program of LPDP as part of the collective effort to strengthen international academic collaboration and research development in Indonesia. We are truly honored to have distinguished participants from various institutions and countries joining us today, and we hope this conference becomes a meaningful platform for academic exchange, collaborations, and inspiration. Ladies and gentlemen, to begin this opening ceremony, let us together sing the national anthem of Indonesia, Indonesia Raya. Ladies and gentlemen, please rise.
We bridge research, innovation, and real-world applications by
Thank you. Ladies and gentlemen, please be seated. Ladies and gentlemen, to warmly welcome you all as guests and celebrate the richness of Indonesian culture, we are pleased to present Tari Gambyong, a traditional Javanese dance. Tari Gambyong symbolizes fertility, gracefulness, and respect, where its elegant and gentle movements reflect the hospitality and warm welcome to the host, to all honored guests present today. Ladies and gentlemen, please enjoy the performance.
Generators and sustainable energy systems. IMS is more than an organization. It is a platform for connection, a center for development, and a force for innovation. Indonesian Magnetic Society.
Ladies and gentlemen, please give a big round of applause for the wonderful performance of Terry Gambiong. Thank you, ladies and gentlemen. Now we shall proceed to the opening remarks session. First, we would like to invite the chairman of the 4th International Conference on Magnetism and its Application 2026, Professor Ahmad Taufik, to deliver the opening remarks. To the Honorable Professor Ahmad Taufik, the floor is yours.
Language, Universitas Negeri Malang continuously strives to improve. Faculty of Mathematics and Science has 4 departments consisting of 10 undergraduate study programs, 8 master's study programs, and 4 doctoral study programs.
Faculty of Economics and Business.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Innovative research, quality publications, and a
Very
synergistic
good
learning
morning,
system.
Honorable Rector
Faculty of Engineering, focusing on the study of
Vice
technological
Rector
advances
One,
can be accessible
Professor
engineering, web
Dr.
research, and international
Ibrahim
facilities, educational, university,
Vice Rector
and professional
Professor Dr. Markus Diantoro, State University of Malang, Honorable Dean of the Faculty of Mathematics and Natural Sciences, Professor Dr. Hadiswano, respected President of Indonesian Magnetic Society, Professor Dr. Agung Nugroho, distinguished keynote and invited speakers, presenter and participant, ladies and gentlemen. On behalf of the organizing committee, it is my distinct honor and great pleasure to warmly welcome all participants of the 4th International Conference on Magnetism and its Application ICMIA 2026. We are delighted to welcome distinguished scientists, researchers, and professionals from various institutions and countries to this prestigious international forum. The 4th ICMIA 2026 provides a platform to strengthen scientific collaboration, exchange innovative ideas, and advance research in magnetism and application for the benefit of the global scientific community. This conference is organized in collaboration by the Department of Physics, Faculty of Mathematics and Natural Sciences, State University of Malang, together with the Indonesian Magnetic Society, IMS, and is supported by many leading universities such as Bandung Institute of Technology, Gajah Mada University, University of Indonesia, Diponegoro University, 11 Maret University, 10 November Institute of Technology, Surabaya, and other collaborating institutions. This conference serves as important platform for researchers and scholars to exchange ideas, present recent scientific findings, and strengthen academic networking and future collaboration. To growing field of magnetism research and its application continues to contribute significantly to scientific
Faculty of Sports Science.
advancement and
As the only
technological
sports faculty in the
innovation
city, it
across many interdisciplinary fields. We are deeply honored to have our distinguished keynote speakers, Professor Masaki Fujita from Tohoku University, Japan, Professor Cheng Hao Chuang from Tamkang University, Taiwan, Professor Dr. Mi Jin from the Institute of Basic Science, South Korea, Professor Koji Nakamura from Mie University, Japan, Professor Worawat Mifasana from Sunirada University of Technology, Thailand, Professor Muhammad Safwan Abdul Aziz from University Technology, Malaysia, and Professor Markus Diantoro from State University of Malang. We also extend our appreciation to all invited speakers, presenters, and all participants from various countries and institutions for your active participation and scientific contribution. Your presence here is essential to making the 4th ICMIA 2026 a meaningful and impactful international academic forum. In particular, I would like to express our great appreciation to the equity program of the Indonesia Endowment Fund for Education Agency, the Ministry of Finance of the Republic of Indonesia, State University of Malang, and the Indonesian Magnetic Society for their significant contribution, financial support for this conference. We also sincerely thank to State University of Malang, IMS, collaborating universities and institutions, and all supporting partners
Mission to
for
lead
their
in providing
continuous
higher
support
education
and
services
commitment.
by opening 4
Finally,
departments that will develop knowledge
I
and
would like to
technology
express
in the
my
field of
deepest
health and
appreciation to all members of the organizing committee, technical team, and support staff for their dedication, professionalism, and hard work through the preparation and execution of this conference. Without your commitment and collaborative spirit, this conference would not have been possible. We sincerely trust that this conference will inspire meaningful discussion, deepen future collaboration, and make significant contribution to science and technology for the betterment of humanity. We deeply appreciate your participation and support. Once again, thank you very much for your contribution. Wassalamualaikum warahmatullahi wabarakatuh.
has 2 study programs.
Thank you very much,
Bachelor's
Prof.
degree
Taufik,
in
for the
psychology
inspiring
and
remarks.
master's degree
Ladies and
in
gentlemen,
educational psychology.
next we would like to invite the President of Indonesian Magnetic Society, Professor Dr. Agustinus Agung Nugroho, to deliver the welcoming speech. To the Honorable Professor Agustinus Agung Nugroho, the floor is yours.
Ladies and gentlemen,
the development and service of
distinguished
vocational
guests
learning,
and colleagues,
producing applied bachelors.
welcome to the
School
International
of Postgraduate
Conference on
Studies.
Magnetic
School
Society,
of-
Magnetics and its application, ICMIA. Let's thank God for His mercy and blessing that we can gather this place and have this event. It is an honor for me to welcome you in Indonesia and welcome to ICMIA conference. The first ICMIA in 2019 was held in Bali, and second one, 2019 was in Solo, the first one. The second one, 2022, it was in Bali, and then this is the one after the pandemic. so we can survive after pandemic. And 2024, we have ICMIA in Jogja. And today, we have ICMIA in Malang, so 2026. So this conference represents a unique opportunity for us to share our knowledge, exchange idea, and build collaborations. So firstly, I would like to extend my gratitude to organizing committee led by Professor Ahmad Taufik. It's very hard work and to make this event possible. So your all dedication and a very hard work, very truly appreciated. Secondly, I want to acknowledge our keynote speaker, invited speaker, and presenter who will share insight and their expertise with us. Your contributions are so important, and we are eager to learn from you all. So lastly, I encourage all of you to take a full advantage of this conference, especially for students. Please eager to involve in discussion and ask questions and find your
Postgraduate
network.
studies at Universitas Negeri
This is the time
Malang
for
offers
collaborations
opportunities for students.
and to grow, and I'm confident that each of us will live here, inspire and enrich. So after seeing this dance, I also already inspired.
To develop
So
knowledge
I
and skills
imagine
in
that
various
this
fields
dancer
of education.
are magnet.
As a result of
So
this
magnetic moments
Universitas Negeri
are
Malang
spin.
has earned the title of Best
So when we
University,
dance,
achieving
see
the first
this,
rank in the ICMIA
magnets.
institution's rankings.
So the dynamics of spins and the movement of the spins. Yeah? So this gambyong is actually a dance from my city, Surakarta. And this is a dance where the farmer will start the planting, and they will expect that what they plant will grow and give prosperity. So when we imagine that the spins are moving and give a dynamics, they're going move back forward. So I think that's probably already inspired us. Maybe there's a kind of a magnetic structure that could be something like that. So we have to find maybe each magnet has a different magnetic moment, different balance. So maybe they can dance also and give us prosperity in the future. So thank you for being here, and let's make this conference memorable and impactful experience for us, and may God always be with us and bless our event. Thank you.
Thank you very much, Prof. Agung, for the insightful speech. Now, ladies and gentlemen, it is our great honor to invite the Vice Rector 1 of Universitas Negeri Malang, Professor Dr. Ibrahim Bafadel, MPT, representing Director of Universitas Negeri Malang, to deliver the address. To the Honorable Vice Rector 1 of Universitas Negeri Malang, with all due respect, the floor is yours.
Field in Indonesia. By continuing this commitment, Universitas Negeri Malang hopes to create inclusive.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. His Excellency Vice Rector for Research and Community Service, Professor Dr. Markus Diantara, also as a keynote speaker for this conference. His Excellency, the Dean of Faculty of Mathematics and Natural Science, Professor Hadi Suwono, thank you very much for your great preparation for this conference. Distinguished keynote speakers and invited speakers, Honorable Chair and members of the organizing and scientific communities, the esteemed colleges, researchers, and students, and ladies and gentlemen. On behalf of the entire academic community of Universitas Negeri Malang, it is my great honor to immerse pleasure to extend the warmest welcome to all of you for the 4th International Conference on Magnetism and its application, or we call the 4th ICMIA 2026. We are profoundly delighted to host this prestigious gathering right here in Malang, a city that has long been a center of education, culture, scientific excellence in Indonesia. Universitas Negeri Malang is deeply honored to serve the venue of this conference. Since its founding, our university is champions the value of religious scholarship, open scientific inquiry, and international collaboration. Welcome the 4th ICMIA 2026 community to Graha Cakrawala is not merely a logistic privilege. It is a reflection of our long-standing commitment to advancing science and technology for the benefit of humanity. We take great pride in providing the space where the brightest mind in magnetism research from across the Asia-Pacific region and beyond can meet, collaborate, and inspire one another. The field of magnetism and its application occupies a unique and indispensable position at the crossroads of fundamental science and transformative technology. From the development of advanced functional magnetic material and magnetic disk form to breakthrough in nanoparticles for biomedical application, magnetic sensor, and superconductivity, the frontiers of this discipline continue to expand in ways that reshape industry and improve the life. The theoretical and computational advancement principles at this conference, such as this one, are the very seed from which tomorrow's innovation will grow. Ladies and gentlemen, I am particularly heartened by remarkable breadth of international participation we witnessed today. Distinguished keynote speaker, invited speaker, and presenter, also researcher and scholar. We have journey for Indonesia, Japan, Malaysia, Singapore, Thailand, Taiwan, and South Area together under one roof in the spirit of shared scientific purpose. This diversity is not simply a statistical achievement. This is the very soul of what makes the 4th ICMIA 2026 a truly global forum. When scientific from different nations from different culture and institutions come together, the exchange of idea transcend disciplinary and geographical boundaries, giving rise to collaboration that none us could have created alone. I extend my heartfelt appreciation to the Indonesian Magnetic Society IMS, and to the chair of the organizing committee, Professor Ahmad Taufik, and team together, with all committee members for this tireless dedication in making for the fourth ICMIA 2026 a reality. Organizing of international conference of this celebrate demand extraordinary effort and the meticulous care that can go into curating a distinguished lineup of keynote and invited speaker. To our distinguished keynote speaker and event speakers, the first is Professor Cheng Hao Chuang, from Tangkang University. The second is Dr. Mi Jin Jin from the Institute of Basic Science of South Korea. The third is Professor Koichi Nakamura from Mi University. The fourth, Professor Makashi Fujita from Tohoku University. And the fifth, Associate Professor Worawat Mifasana from Sorineri University of Technology. And the sixth is Associate Professor Dr. Muhammad Safwan Abdul Aziz from University Teknologi Malaysia, and also Professor Dr. Markus Diantoro from Indonesia, especially from Universitas Negeri.
Footprint. UM adopts various environmentally friendly practices.
Circle and to return to your laboratories and classroom with renewed connection, energy and broader vision. The conference proceeding, journal publication and the connection you force here today will serve as resource you draw upon for years to come. It is our sincere hope that the 2 days of the 4th ICMIA 2026 will prove not only intellectuality enriching, but also personally memorable. Malang is the city of warmth, natural beauty, and rich culture, and we invite you to experience its hospitality during your visit. In closing, gratitude of Universitas of Negeri Malang to all participants, organizer, sponsor, especially equity from LPDP Indonesia Endowment Fund for Education Agencies, Ministry of Finance of Republic Indonesia, and sporting institution for who have made the fourth ICMIA 2026 possible. We wish this conference very success and look forward to celebrating the discoveries and collaboration that we emerge from it. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Ladies and gentlemen, to seek blessings and a smooth proceeding for today's conference, let us now have a prayer together. The prayer will be led by Mr. Nurul Hidayat PhD. To Mr. Nurul Hidayat PhD, please come to the stage.
Because UM will continue to be a place.
Assalamualaikum warahmatullahi wabarakatuh.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Distinguished delegates, ladies and gentlemen, let us now bow our head for a moment to pray to God, Allah Subhanahu wa Ta'ala, so that our international conference today and tomorrow can be precious to all of us. And allow me to lead this prayer based on the Islamic teaching. A'udhu billahi minasyaitanir rajim. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Hamdan yuwafi ni'amahu wa yukafi mazidah. Ya Rabbana lakal hamdu wa lakal syukru kama yanbaghi li jalali wajhikal karimi wa azimi sultanik. Allahumma salli wa sallim ala sayyidina Muhammadin wa ala alihi wa sahbihi ajma'in. Allahumma inna nas'aluka salamatan fid din wad dunya wal akhirah wa afiyatan fil jazad wa ziyadatan fil ilmi wa barakatan fil rizqi wa taubatan qabla al maut ورحمة عند الموت ومغفرة بعد الموت والنجاة من النار والعفو عند الحساب برحمتك يا أرحم الراحمين. Ya Allah, Ya Aziz, today and tomorrow, in this wonderful time and space and place, we gather here to bring about the 4th International Conference on Magnetism and its Applications 2026. Ya Allah, Ya Rahman, please make this international conference as a useful science assembly, as a medium of sharing useful ideas, knowledge, and experiences of scholars, researchers, and students from various institutions. May the conference we organize today benefit to our lives, broaden our knowledge, and
Positive change in local and global communities.
Good morning, distinguished keynote.
which in turn will boost the dignity of our nation and for the better future of the planet we live in. ربنا أتمم لنا نورنا واغفر لنا إنك على كل شيء قدير. Ya Allah, Ya Kareem, perfect our light for us and grant us forgiveness, guide and bless our hearts and our minds with the light of your guidance. Impart your supreme wisdom upon our activities and help us to be the blessed persons. ربنا آتنا في الدنيا حسنة وفي الآخرة حسنة وقنا عذاب النار وصلى الله على سيدنا محمد وعلى آله وصحبه وسلم. سبحان ربك رب العزة عما يصفون وسلام على المرسلين والحمد لله رب العالمين. والسلام عليكم ورحمة الله وبركاته.
Speakers and invited guests. The Honorable Rector of Universitas Negeri Malang, which on this occasion is represented by Vice Rector Huan, Professor Dr. Ibrahim Bafadel, MPD, along with the distinguished members of the University Board of Universitas Negeri Malang, the President of Indonesian Magnetic Society, Professor Dr. Agustinus Agung Nugroho, the Chairman of the President of Indonesian Magnetic Society, the Chairman of ICMIA 2026, and distinguished keynote speakers. Once again, we would like to invite the Vice Rector 1 of Universitas Negeri Malang, the President of Indonesian Magnetic Society, the Chairman of ICMIA 2026, and distinguished keynote speakers to come to the stage. The 4th International Conference on Magnetism and its Application, Professor Ahmad Taufik, the Honorable Keynote Speakers, Professor Cheng Hao Chuang from Tamkang University, Taiwan, Dr. Mi Jinjin from Institute of Basic Science, South Korea, Professor Koji Nakamura from Mie University, Japan, Professor We would like to invite also Dean of Faculty of Mathematics and Natural Science. Once again, Dean of Faculty of Mathematics and Natural Science. And the Head of Department of Physics. Once again, we would like to invite also the Head of Department of Physics, Faculty of Mathematics and Natural Science to come to the stage. Diantoro from Universitas Negeri Malang, Indonesia, Profesor Mas Saki Fujita from Tohoku University, Japan, Professor Warawat Mifasana from Suraneri University of Technology, Thailand, Professor Madhya TS, Dr. Muhammad Safwan Abdul Aziz from University Technology Malaysia, respected invited speakers, professors, researchers, academicians, participants, and distinguished guests. Ladies and gentlemen, on behalf of the organizing committee, it is my great pleasure to welcome you all to the 4th International Conference on Magnetism and its Applications 2026. Ladies and gentlemen, please, we will have a formal pose. Ladies and gentlemen, it's me at the photo session. 1, 2, 3. Next, please, we would like to invite everyone to at 2026 serves as an international scientific forum that brings together researchers, scientists, academicians, and practitioners to exchange knowledge, discuss recent developments, and strengthen collaboration in the field of magnetism and its application. We are also proud to share that this conference is supported by the Equity Program of LPDP as part of the collective. Please, you may come to the And please to invited speakers, you may stand up and join the group photo session. And to all participants, effort to strengthen international academic collaboration and research development in Indonesia. We are truly honored to have distinguished participants from various institutions and countries joining us today, and we hope this conference kita foto bersama menghadap ke depan panggung. Once again, please stand, everyone. Dan merapat ya, Bapak Ibu, merapat silakan. Sekali lagi bisa merapat, Bapak Ibu yang di belakang merapat, kita ke tengah sedikit. Oke, merapat sedikit Bapak Ibu yang di belakang. Becomes a meaningful platform for academic exchange, collaborations, and inspiration. Ladies and gentlemen, to begin this opening ceremony, let us together sing the national anthem of Indonesia, Indonesia Raya. Ladies and gentlemen, please rise.
1, 2, 3. And next, please, the only one.
We bridge research, innovation, and real-world applications by...
Wonderful. Okay, IMS. Yeah. Okay, please. IMS gesture. Okay. University, Japan in 2003 and received a PhD degree from Nagoya University, Japan in 2006. He was appointed as a postdoctoral researcher for 5 years since 2006 until 2011 at Nagoya University and Nagoya Institute of Technology, Japan. And we have our next moderator, which is Professor Dede Juhana. He is professor at Department of Physics, Faculty of Mathematics and Natural Science, Universitas Indonesia. He graduated from doctor program in 2010 from Department of Physics, Chungbuk National University, Chengdu, South Korea. And we also have Professor Ristiana. He is a professor in the Department of Physics, Universitas Pajajaran. He obtained his PhD from Department of Applied Physics, School of Engineering, Tohoku University, Sendai, Japan, in 2006. In 2008 until 2011, he did a postdoctoral with the Foreign Postdoctoral Researcher, or FPR scheme at Riken Nishina Center, Japan. And that was a brief introduction of our moderators. Thank you very much, ladies and gentlemen, and please enjoy the conference. Wassalamualaikum warahmatullahi wabarakatuh.
Merdeka,
Thank you. Ladies and gentlemen, please be seated.
Contribute.
Ladies and gentlemen, to warmly welcome you all as guests and celebrate the richness of Indonesian culture, we are pleased to present Tari Gambyong, a traditional Javanese dance. Tari Gambyong symbolizes fertility, gracefulness, and respect, where its elegant and gentle movements reflect the hospitality and warm welcome to the host, to all honored guests present today. Ladies and gentlemen, please enjoy the performance.
Generators and sustainable energy systems. IMS is more than an organization. It is a platform for connection, a center for development, and a force for innovation. Indonesian Magnetic Society.
and gentlemen, please give a big round of applause for the wonderful performance of Terry Gambiong. Thank you, ladies and gentlemen. Now we shall proceed to the opening remarks session. First, we would like to invite the chairman of the 4th International Conference on Magnetism and its Application 2026, Professor Ahmad Taufik, to deliver the opening remarks. To the Honorable Professor Ahmad Taufik, the floor is yours.
Language, Universitas Negeri Malang continuously strives to improve. Faculty of Mathematics and Science has 4 departments consisting of 10 undergraduate study programs, 8 master's study programs, and 4 doctoral study programs.
Faculty of Economics and Business.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Innovative research, quality publication, and a
Very good morning, Honorable Rector
Faculty of Engineering focuses on the study of
Vice
technological
Rector
advances of canvas accessible
Professor
engineering,
Dr.
research and facilities
Professor Dr. Markus Diantoro, State University of Malang, Honorable Dean of the Faculty of Mathematics and Natural Sciences, Professor Dr. Hadiswano, respected President of Indonesian Magnetic Society, Professor Dr. Agung Nugroho, distinguished keynote and invited speaker, presenter and participant, ladies and gentlemen. On behalf of the organizing committee, it is my distinct honor and great pleasure to warmly welcome all participants of the 4th International Conference on Magnetism and its Application ICMIA 2026. We are delighted to welcome distinguished scientists, researchers, and professionals from various institutions and countries to this prestigious.
So next one, please. Next one, please. The other way is just to apply for the external electric field temporarily to reduce for the energy barrier, I mean the PMA, from the top, reduce for the MCA. Next one, please. So I want to move to the first topics, perpendicular magnet anisotropy, PMA, and the magnet damping in ion MGO system. Please, next. Next, please. Okay. Before I show you my result, this is the trend in the PMA in horizontal axis, I mean the K, and also the vertical axis is a damping constant. So we cannot see. So the trend is going to be positive slope from the bottom to right, like this one. Next one, please. Okay, so even in Heusler alloy, it's fine, very good. Still the slope is positive. So the target for the device application means the largest PMA and the lowest alpha. Okay, next one, please. So we try to find for the we try to interface modification this MTJ model. So we just to substitute for the oxygen to the nitrogen and fluorine. So nitrogen is look like the hole doping, and fluorine is look like the electron doping. So next one, please.
So this one is my calculations I use for my full potential linearized argument plane wave method within the GGA. And also the magnetic crystalline anisotropy energy is calculated by the Horst theorem. And also the magnetic Gilbert damping constant is calculated by Campbellsky torque correlation model. Next one, please. So this one is some result for the PMA and damping. So first of all, this is pristine ion MGO system. So the red one is MCA energy, and then this shows the positive number about around to the 0.5. It shows the PMA, and alpha damping constant about 1.6 to the 10 minus 2. And next one, please. And the left one is a nitrogen insertion. The right one is a fluorine insertion. Next one, please. So here the MCA or PMA increase about 40%. Next one, please. And the damping constant is reduced. So we achieve for the high PMA and low damping. Next one, please. So this is a band structure of the D state of the ion at the interface for the pristine cases. The lower figure, below the figure, shows the energy diagram. So you can see the ion D0 and the oxygen P0 hybridized, and then so it make the bonding and anti-bonding state, and at the Fermi level, D plus 1, D plus minus 2 remain on the Fermi level. Next one, please. In the nitrogen insertion, because of this look like the whole doping, therefore the P state in nitrogen is moved to be Fermi level. In the case we have additional hybridization. So this is the D plus minus 2, D plus, so I'm sorry, D. Okay. The additional interaction D plus minus 1 and P plus minus 1 to make a bonding and anti-bonding. At the Fermi level, we have only the D plus minus. Next one, please. So according to the second perturbation theory, the interband contribution between the D plus minus 2 and D plus minus 2 enhance the PMA. Also the separation between the D plus minus 2 and D plus minus 1 reduced for the alpha. Okay, next one, please. So additionally, I calculated for the barriers for the interface. And then, first of all, I said we achieve for the high PMA and low alpha simultaneously. Next one, please. So we can overcome the trade-off. You can see, probably we cannot see for the line. There is a line from the negative slope. I'm sorry. Okay, next one, please. And also we got for the target. So target achieved candidate for the interface modification is a nitrogen insertion and boronite lithium fluoride. Okay, next one, please. So I want to move to the next topics, VCM in ion MGO system. Please, next. So this is a trend in the experiment. So now to be horizontal axis here, vertical axis show the VCMA constant defined over there. So first of all here show the typical of the MTJ sample, the cobalt iron boron cases. It show around for the 100 femtojoule per voltmeters. Next one, please. And so here using for the heavy metal, inserted and also the capped layer. So this is increase for the about for the 300 femtojoule per voltmeter. Next one, please. So next one, please. So the several attempts there is, but the still the VCMA coefficient constant is around for the 350s. So the in the device level, it required, people say its requirement is around for the 1,000 femtojoule per voltmeter. Next one, please. So we try to, first of all, understand for the VCMA using for the pristine model, ion and MGO system. So we introduce for the linear potential from the vacuum to vacuums. Next one, please. So this is the result. So the horizontal axis is electric field. Vertical axis, the MCA energy. Here I normalize by the zero electric field on that equations. So you can see as electric field increase, it's linearly, the MCA energy increase, it's almost linearly. So from this slope at the zero electric field, we can obtain number. This is a VCMA constant. We have the 32 epsilon. Epsilon means the electric constant of perpendicular directions. So it shows the horizontal axis is m, gamma, m prime. So m prime is a minus m directions. Okay, the around Fermi level 0, we can see the D and P hybridized band dispersion. Indeed, at the gamma point, we have a symmetric dispersion. Next one, please. When going to be magnetization orient to in-plane direction, it's rather interested. So it shows for the negative K, I mean M prime directions. So energy, eigen energy is decreases. But the positive side, so M side, the eigenstate, eigen energy is go up. It shows the asymmetric dispersion. Okay, next one, please. So this one is commonly known about the Rashba effect. There is a Rashba effect in the ion MGO system. So this is, you can easily understand for the spin of the coupling Hamiltonian, sigma directed for the in-plane direction. The electric field direction is out of plane direction. This cross product is in plane direction. Therefore, we can obtain for the asymmetric energy dispersion. Next one, please. So we try to understand for this Rashba splitting from the asymmetric wave function. Probably we can describe for the Rashba splitting on the path line. And then I just inserted for the SOC Hamiltonian, and also I use for the wave function of the free electron model. And finally, we can get for the second equation. So dV divided by dz is correspond to the electric field, and the last one, m k, is magnetization density. Next one, please. So when you're looking for the magnetization density, the red one, so at the ion side, we can see asymmetric magnetization distribution. This gives some Rashba splitting. Next one, please. So next one is I try to roll for this VCMA via the interface modifications. So I try to insert it for the aluminum nitride, lithium fluoride. Next one, please. So based on the electronegativity difference because of the ion MgO, it has a 2.13 and aluminite is a 1.43 and lithium fluoride is 3.00. This shows the how much tips of the p state on the described on the right side of figures. Next one, please. So this is the result. So you can see the black circle show the pristine, and the red one is aluminum nitride insertion, and the green one is lithium fluoride insertions. So we obtain for the linear relation. And next one, please. By this slope, this summarizes for the VCMA constant. If you introduce for aluminum nitride, we have a 45 epsilon, and the lithium fluoride insertion 22 epsilon. So the aluminum nitride case is it's enhanced 40%, and the lithium fluoride is it reduced for the 30%. Next one, please. So I extended for the calculation to include some several insulator insertion. Next one, please. So the horizontal axis show the MCA energy, I mean the PMA. Vertical axis is the VCMA constant. So when looking on this figure, the increase of the MCA result in decrease in the VCMA. However, the target for the device is about for the 1,000 femtojoule per voltmeter with a high PMA. However, this result show that we cannot obtain we cannot overcome the trade-off relations. Next one, please. Okay, it's almost time. This one, last one. Thank you so much. So I want to summarize for my talk the perpendicular magnet anisotropy PMA and the magnet damping in ion MgO system. The trade-off can be overcome. The result predict that hole doping ion MgO nitride MgO achieve a large PMA and low magnet damping simultaneously. For the voltage control magnet anisotropy ion and MgO system, VCMA is driven by the Rashba type band splitting, and ion, aluminite, and MgO model enhance VCMA coefficient. However, the trade-off may be unavoidable. Thank you so much.
Give applause. Okay. Even you have still 10 minutes. Okay, please.
I'm sorry.
Yeah, it's okay. Okay. And for the next speaker is Professor Cheng Hao. Okay. He is currently professor in the Department of Physics in the Tamkam University in Taiwan. He obtained the PhD from the National Taiwan University, and his research interest in the synchrotron X-ray spectroscopy and also photoelectrics, something like that, for the environmental application. And he's talked about the combining ferromagnetic nanoparticles with graphene oxide. Is right? Okay. Please start.
Okay, thank you. Thank you so much. It's my honor to be here, and thank you the organizer AD to invite me come to here. This is my second time to visit Indonesia. So my title here is very simple. Actually, I combine the graphene oxide membrane and also some traditional metal nanoparticle, and for the ferromagnetic application and catalytic applications. Next one, thank you. So I think not all the ones know the Taiwan, but we just very close to Japan, China. So I think that recently everyone knows that President Trump always mention Taiwan stole the semiconductor IC chip from America, right? So I think everyone knows where's the Taiwan, and somehow President Trump and President Xi Jinping already had meetings in the last week, right? So always mention the Taiwan problem. Okay, well, I don't know, we have the problem here. Anyway, so this one, you can see we have also famous Chiang Kai-shek membrane hole. So I think some professor is already visited Taiwan, and the other one is for our Tankang University. We are on the hill, so we can see the Danshui River, and the other one. Thank you. The next one. Okay, yeah, I think someone's like to drink some bubble tea, oolong tea, and also see some Taipei 101. And also we also have the one special one, the Ali Mountain is for high mountains, the railway train. It's a very, very well to see. Okay, the next one. Okay, so this is my outlines. So here I will show you some membranes, the fabrication method, including the graphene oxide membrane, reduced graphene oxide, and I will put some nanoparticle. For example, iron oxide nanoparticle, copper oxide nanoparticle inside this membrane. And for the applications, I will try to convince you this one catalyst is good for the hydrogen evolution reaction, carbon dioxide reduction. And in this talk, I will using some unique instruments. For example, the scanning transmission X-ray microscope, ambient pressure X-ray photoelectron spectroscopy, carbon pole force microscopy, and also some X-ray magnetism, current, dicoherence measurements. Okay, the next one. Okay, so this is my part one. I will try to and then you know how can we prepare our membranes using a very simple way. And the second one is how can we know the list? How can we know the list graphene oxide membrane? We can use some X-ray absorption spectrum to identify, to catalyze the surface potential and the surface catalyzation, and also some oxygen functional group on the surface. And we try to do the in situ, the heating in situ experiment for this one. So we can, the final application will show you some water permeability and the carbon dioxide selectivities, like this one. Okay, the next one. So how can we grow graphene oxide? I think almost 20 years ago, everyone knows how to grow graphene oxide using some noble metal catalyst put into the CVD, chemical vapor deposition, and you can grow in the graphene materials from the list catalyst metal. The next one. Graphene oxide material. So we also developed some different methods. We start to make to fabrication the graphenes from the graphene oxide membrane. So 1956, I do remember, they have some Hermes method. They try to using a very strong oxidation solution to oxide the graphite, and the graphite will become separate. But somehow the surface have a lot of oxygen functional group. So the problem is how can we make the graphene? How can we reduce graphene oxide? So they have a lot of methods. You can try to use in the hydrosimos reduction. And then the other one, the next one, our method in our lab, we try to use in two different methods. The first one is the chemical reduction, GO. The other one, the simple reduction, GOs. The next. So we were using some DFT calculation, serial calculation to identify the cell potential and identify its wall function. And we also using the X-ray microscope to measure the functional group of distributions. The next one. So in the beginning, how can we grow the graphene oxide? Actually, you can see on the right-hand side, we prepare the graphene oxide solution in the liquid phase, and then we put it into the cell. The next, and we can use in the SEN to measure the flake of the graphene oxide size. For this size, it's around 200 to 600 nanometers. And then the next one, we use in the electrochemical method. So we use in this solution, the dark area, darkest solution into the bottom, and we apply the electrochemical method, working electrode, reference electrode, counter electrode, and we cycle it. We're using the different potential from the negative 1.5 to the 1 voltage, but with a lot of cycle. For example, here is 250 cycles. The next one. Then you can go the membranes on the gold mesh. For example, you can see the Raman data we use a laser point to measure this, the D band and G band, defect band, and the SP2 graphene-like structure, G band. And we also use an AFN, automated force microscope, to measure the thickness of this membrane. So we can see the image layer. We can show you the thickness of this, the graphene, reduced graphene oxide is about 34 nanometer. The next one. And the second method, we use the thermal reduction methods to reduce the graphene oxide. So through this process, we can make a very good reduced graphene oxide flake. So we can make the different shape. This one we call the papers, the flights from our membrane. The next one. And then we also cut this sample. We want to see the cross-section of this reduced graphene oxide membrane. So you can see this one. It has a lot of the layers. It's staking on the surface. And cut this one, and we try. Can you touch the video? Can you run this video in the center? No, the one. Yeah, the one. Thank you. So the ones that you see the very flexible. This flake you can make it larger and also very flexible. So we can make a different shape of this membrane. And then it inspired us how can we use this kind of the physical property to make some new advanced applications. The next one. So in the beginning, we use the Raman microscope to measure the geo, practice geo and reduced geo, but we didn't see any difference on the D band and G band. And we also use SPS, and we find out the reduced one, the CB methods have the decrease of the oxidation state in the high energy side. Even for the oxygen 1S, you can see the decrease of oxidation state. The next one, but this one, I want to show you how powerful of the instrument, scanning transmission distance. We can focus on the X-ray beam with the very, very nano scale, around the 13 nanometer scale, and we can measure the transmission intensity. And depending on the BS low, optical density equal to the intensity ratio, and it will be related to the thickness, the density of this material. The next one. So we can see the very good image, like this one. The left one, you can see the reduced graphene oxide. The bottom one, you can see the drop catch geo. And the important thing is we can select the areas. For example, you can select the area 1, interest area 1, 2, 3, 4 to 6. And we can know which one is the drop cast geo. On the 5 and 6 drop geo, we can measure the latest structure. And we can find out in the beginnings they have a very strong oxidation state. For example, COH. And try to fabrication the different special oxidation species. The next one. And then we are not satisfied on this kind of in situ experiment, but also we want to use in the KPF. Not only measure the surface morphology, but also on the surface potential. Okay, so the formula is like this one. We can use in the tip, the FN tip cantilever to measure surface morphology, and at the same time we apply the potential on the tip. And then we can measure the surface potential. The next one. Yeah, the next, thank you. And we can measure surface potential is what we call the potential difference between the tip and the surface. Okay, the next one. Yeah, the next, thank you. Yeah, the next. Okay, so this one, okay, step here. So we found some interest in the pattern. You can, right-hand side, SEM image, you can see the pattern over there. And we use the KPF, and we can also measure the same areas. So we can find out on the surface morphology, the yellow part, you didn't see any contrast image. But in the color bar and A, B, C, figure C and the F, we can see the patterns is quite similar, identical to the SEM data. And the middle one here, we also measure the drop catch geo, and we can find out his surface potential actually has difference. The figure H have the drop catch geos for his work function is around 5.8. But reduced graphene oxide, you can see that this here. They have the 4 components. And we find out that they have the quite difference in the work functions, the measurement. So I talked to my neighbors, my colleague, about can we use in the DFT calculation to identify the 4 different oxidation states, and here's the wall function. And you find out you can see the 4 different oxidation states, COC, COH, COO, COH. It have the different wall function. So from the high oxidation state to the middle oxidation state, and also graphene, you can see the wall function become from the higher to lowest, depending on the concentrations and also the different species. So next one. The next, yeah. So this one, I show you, if we can control the different functional group, different oxidation state. Actually, we can control the different wall function. Okay, so the next one. The next. Okay, so the second method we use in the thermal reduction one. So we try to use in the dry cast geo, heating the geo membrane in the making, heating geo membrane in the air. So we can see the surface morphology almost very flat, and somehow the surface become from the very rough become very smooth. The next one, and the next, and also we use in the FTIR microscope to measure the 3 different to measure the vibration modes of the 3 different these 3 different material. For example, geo, thermal reduction in making, thermal in air. So we can find out the next one. They have the, okay, anyway. So they have the decrease of functional groups by our FTIR measurement. And here I show you the other technique. We use the ambient SPS to heating the substrate to control the gas environment. For example, the different gas species and also with the different pressure. So we use the synchrotron to using the synchrotron X-ray, very high brightness X-ray. And we measure our samples in this Taiwan light source B924. And this is our sample in the middle. This one is our sample. We have some golden mesh, have the sandwich. On the top is the graphene outside membrane, on the bottom also. And we put in the substrate, and we're heating our materials from the room temperature to the 300 degrees C. And we can see the decrease of functional group around the 288. And then we also control we also can measure his carbon absorption, carbon 1s, the co-label spectrum, the next one. And we also measure oxygen sites. So we can find out from the room temperature to the higher temperature, it decreased. And we're using the curve fitting to identify the 4 different functional groups. The higher impact for the functional group is like the COH and the COC in the middle. Okay. Then the next one, we also, that's the conclusion, but I don't have time, so go to the next one. Yeah, we also control the gas environment. For example, we annealing this one in the making, in the air, but we control the nitrogen and oxygen ratios. Still, you can see the very similar formulas through this thermal reductions. You can see the decrease of functional group with the curve fitting result with the 4 different functional group. In the oxygen side, you also see the decrease, but somehow you can see this one. In the oxygen side, they have the different ones. It means when you control the gas environment, actually you can control the gas species. For example, the last one, similar RGO air, you can see the strong intensity in COO and the COC. But they have the highest decrease reduction part in the COH and the COO after 300 degrees C. The next one. And this one, I will show you the TPD, temperature programming distortions. So we use the mass spectrometer. We use some special thermal annealing platform to anneal our substrates in the making. Okay, the figure A over there is we just heating our metal, heating our system without any substrate. The figure B is we put the graphene outside membrane. So I can find out we have the first one, we can see the very strong intensity distortions, the intensity of the distortions in the water's molecule around the 225, 200 degrees C. And then when we go into the 200, we also see some new distortion gas species, for example, C monoxide, C dual oxide, CO2. And then the next one, after annealing, we put it into air again. And we want to see is there any possible to see the new associations on the reduced graphene oxide material? And we do the mass spectrometer again, TBD again. I can find out the water molecule still can attract onto the thermal reduction GO. But somehow the CO2 of the COs also happens depending on the making system of air systems, linear systems. So we can see the difference here. The next one. So this experiment is also a new one. We're using the membranes for the in situ liquid cell. We put our membrane, you can see in here, inside, just in the hole on the top of the making chamber. And we throw the liquids over there. We throw a liquid. And then the liquids, the water molecules can be sucked into the making system because we give it a pressure. So we can see the flow of have the very low pressure, partial pressure, but when you give it some pressures by the outside, then you can see the increase of the water molecule signals going to up. And we try the three different materials. They have three different response. And then the next one. Yeah, the reason we can see the water permeation through this membrane because the surface have some structural defect, making the areas inside. So you can see using the hydrogen TEM result, you can see there's some small hole in the GO, and higher densities the holes in the air, and very larger size of the empty areas in the small GOs make it. Okay, the next one. Okay, this is some discussion, short discussion, because we know the graphene is quite close around the 3.2 angstrom. But if we put some different oxidation state, like COH, COC, actually it will expand the interlayer distance. The next one. And this one, the interlayer distance is open, is very important for the water permeation. And also the lattice defaced overlayer is also very important. We call the nanoporous hole for the GO's membrane. The next one. And the next one, we expect to see some space, some empty area, and also some different function group over there. So different function group have a different charge, positive or negative or strong negative one. So you also influence some charge interactions, like current interaction, and the size of the hole also will be influenced the gas species because of the size. Okay, so this one is geomembranes. We can control different function group and the different space for water transportation, for the carbon dioxide absorption. Later I will show you. The next one. Okay, this is the second part. We want to put some transition metals into these membranes because we want to have some cooperation with the manganese society. So, but this one is for catalytic applications, for hydrogen evolution, ocean evolution, for example. The next one. The next, yeah, the next. So this one is for hydrogen evolutions. We call the volcano plot, depending on the different metals species. The middle one is a PT palladium. It's a very expensive. It's a noble metal. The left one is the cobalt nickel ion. It's a cheaper one, but also very important for the ferromagnetic property. The next. So according to the calculation, theoretical principle calculation, we can know the strong binding for pseudo binding for hydrogen and the weak binding hydrogens. The next one. So we can go over this one. We can know the very weak bindings for the cobalt nickel transition metal, but strong binding for the titanium, tungsten metals. The next one. The next. The next. Next. Yeah. So the next. Okay. So this one, because we gross some nanomaterials with some transition metals, the 3D transition metal. So actually also offer the different property, magnetic property. So we can observe some spins, the distribution, magnetic field distribution, even some d electrons contribution. So a lot is it is second topic. Actually, I will more combined on the 3D electron and also distribution and also its the ferrochemical properties, which connect to the catalytic reactions. The next one. So this one, we published these papers 2 years ago with the National University of Singapore. So they find out they have some special materials, the molybdenum disulfide material. But when they goes the nickel atom into the molybdenum disulfide materials, when they can apply the ferrochemical field, and then they can increase the oxygen evolution reactions. So you can find out if you don't have any external magnetic field outside, then the currents of the OER is quite low. But when you apply the external magnetic field, you can increase oxygen evolution reactions, and also you can see the very highest oxidation current intensity. The next one. The next. Yeah. So in our synchrotron X-rays, you can see the video over there. So you can see the bubbles from the electron. Okay, so in our Taiwan synchrotrons, actually we can do the measurements. We apply the magnetic field, and we can find out if you don't have any magnetic fields, you just have the very similar spectrums. But when you apply the strong magnetic fields, you can see the shift of the list bondings. So it means that we actually using the external magnetic field to increase the higher density state, which is near the Fermi level. And then we also apply the potential to do the oxygen evolutions, for example, 0.8 voltage on the surface. And then so we can see the new features on the shoulders. Now, next one means that they have the very strong correlations between the sulfur 3P and the nickel 3D density. So you can see the increase, the ones in here. Okay, so that's the very strong evidence. So then we published this paper in the National Nanotechnologies journal. Okay, the next one. Okay, so this one I will show you very fast. Like we also grow the cobalt on the RGO's surface. So in the beginning, we just using the circular attachments to grow the graphene oxide flake on the surface. So you can see this one. You can see the very dark areas on the surface. This one is belong to the reduced graphene oxide membrane. After that, we grow the cobalt by also the electron method. We can grow the cobalt on the surface. So in the SEM data here and here, you can see the quite difference without any RGOs. And we also use the Raman data, Raman measurement to identify they have the cobalt signal around 500 and the graphene the signal around the 1,500, around 1,070. It's make sure that we combine the cobalt, the nanoparticle, and the graphene together. The next one. The next. Next. Yeah, the next. Thank you. Okay, so about the catalytic reactions, the experiments, we also use in the in situ mass spectrometer. We apply the different potentials on the three material. One is the pure cobalt. Second one is the cobalt on RGO, and the other one is for the stainless steel. So on the bottom one, stainless steels, you cannot see any difference with the functional potential. But if you go to the cobalt catalyst, you can see the very strong intensity here. And when you put the extra reduced graphene oxide in between, between the cobalt and the stainless steel substrates, you can see the increase of the hydrogen evolution and also hydrogen signals. The next one. So this one. And this one we will develop into the two phases, phase 1 and phase 2. You will remember this one because I will show you the data on by the spectroscopy, X-ray absorption spectrum, and then you will know what's the reason I want to put some boundary between the phase 1 and phase 2. Okay, the next one. Yeah, so we'll show you the hydrogen evolutions, the reactions happens earliest in the cobalt RGO substrate, and also it offers the very strong hydrogen signals by our cobalt and the reduced graphene oxide hybridized materials. The next one. Yeah, the next one. So this one is the in situ X-ray absorption spectrum. the figure A and B, C is for the copper and gold substrate. The EFG is the copper goes on the RGO substrate. Through the in situ measurements with the functional potential from the little voltage to the negative 1.2 here. So we can see the peak of the copper signal is become to have some evolutions. So you can see the evolutions happen here. But if you cross the RGO on the buttons, actually the copper signal almost the same. Almost the same. So you can see almost the same. And the next one, we do the curve fittings to identify the different oxygen function in the different potential. And you can see the increase on the copper and gold. And the other one is you can see the phase and going down. The next one, we also measure the oxygen one. You can see the very strong bondings on the gold, copper substrates. But if you go to RGOs, they don't have any difference on the first peak, 531. It means they don't have the very strong bondings between the water molecule and the copper. Because that's good things, because if you don't apply the potentials, the catalyst cannot have any reaction between the water molecule splitting and the catalyst metals. That's a good thing. The next one, So we also use a high throughput to do the measurement. It can, through this curve fitting with the standard substrate, then we can see the function average oxidation state will going up, and when you arrive to the negative 1.1, then we go in, the oxidation state will going down. But for our substrate, copper RGO substrates, actually you can see it have some shift from the negative 1.1 to the negative 0.7, have a big shift. Can you go to the next one? Next one. Yeah, the next one. So a while ago, I told you that we have the phase 1 and phase 2. So I already do the assignment. Phase 1 is for the lower potential. Higher one is for phase 2, is for higher potential. Can you go to the next one? The next one. Yeah, this is phase 1. Can you go to the other one? So for the next, yeah, this is phase 1 and this is phase 2. These three reactions that combine the Maurer's step and the Tarford step and the Herbert-Sky step. Which step you can see this chemical reaction? It will depending on the hydrogen bonding, two hydrogen bonding, and become the hydrogen gas out. So we can using our X-ray measurements to identify the potential below the which one. Then you have the very strong bonding for the hydrogen, metal with hydrogen is phase 1. But if we have the very strong the second one going to the next step, second one, phase 2, then the hydrogen become the hydrogen, two hydrogens, the atom out. Then the average oxygen function will become the last because the dissolution of the hydrogen. Okay, the next one. The next. Yeah, sorry, I don't have time, so maybe I go to the next one. I skip this one. Sorry, I skip this one. And the next, sorry, the next, sorry, I have to skip this one. There's more story over here. And this one is for the data calculation. And in this data, you can find out the Herbert-Sky reactions happens become the last due to the RGO substrates here. So you can see the potentials, the barriers difference. So that's the reasons we find out the very highest hydrogen's the production rate, generation rate, because we decrease the energy barrier of the Herbert-Sky reactions. Okay, the next. I just gave some summary here. The next. Okay, so stop here. So as I show you, we have 3 different steps for the hydrogen evolutions. Herbert-Sky reaction actually happens to become larger because our RGO. And through our reduction, in situ measurement and derivative calculation, we know the reasons why we can see the higher hydrogen evolution, because we open the space of the Herbert-Sky reactions. Yeah, the next. We also want to go through some iron oxide nanoparticle for carbon dioxide reduction. And can you go to the next? So we want to combine the GO substrate because they have very strong bondings between the oxygen functional group of the GO, for example, COH with the CO2 gas, OH with CO2 gas. And the ion also is very good ones to absorb the CO2. So we fabrication the ion oxide nanoparticle on the RGO membrane, so you can see the ICEN. They have a small nanoparticle around the 15 nanometers. And you can see around these membranes a lot of nanoparticle. Can you go to next? The next. Yeah, the next. Sorry, this slide. Yeah, you can go the next. So we use the station. Okay, so we can measure the different location 1 to 5, and we can find out where's the location 1 to 5, right? And we selected the area, and we can measure ion, the signal stuff about the ion oxide. Okay, the next one, the next. And we also measure the oxygen parts. We see the very strong bondings in the first step, 131. The next one, because we combine the graphene, we combine the graphene, so we also want to measure the carbons, the signals on this membrane, so we can select a different areas. So I have different functional group in this one, and with some ion, with some oxygens, and also with the different bondings coordination. So the next. This is also conclusion. The next. Okay, so this actually has a movie. If you can play the movie in the window, this one. If you can run. No window. Okay, the next one. Okay, so this one is the new ones that we, in this semester, actually we will find out the simple method to fabrication of some ion nanoparticle. So we combine the GO solution 1 and the ion 2 plus, ion 3 plus ion, and then we mix it together, the next. And then we put into the next. Yeah, the next one, yeah, this one. And we, for the difference, can you run the video over there? This video? Yeah. If you just go mix the GO substrate and the ion 2 plus 3 plus ion in the liquid, we didn't do anything. They don't have any ferromechanical property. Can you go to the next one? Next image. Yeah, this one. Can you run this video again? But this one, we go the process 3 and 4. And we can actually use in the external magnetic field to attract the nanoparticles, something like this one. Okay, the next one, next image. We also can drive this one, and it will become, yes, run this video, thank you. And we also can attract the frag, the dried ones. So we definitely, I think these solutions and the dried ones have the very strong ferromechanical property. Okay, so the next one. And we use the TEM to measure the nanoparticle size. It's around 2 nanometers, 3 nanometers. And here we also use the X-ray absorption spectrum, SNCD, to measure the spin polarization, orbital polarization, and we can find out this one have the 3 different 3D electron coordination on the 2 different sides, T2G and EG side, with the different spins. Okay, the next one. Even though we use the ion graphene oxide with the NaOH solution, we also can fabricate the nanoparticles of ion oxide nanoparticle on the surface and use SNCD, the spectrum. You can see the green one. They have the reverse by the X-ray polarization directions, so you can see the decrease and also increase in the A and the B2 and B3 side. This data also supports our favorite property of the nanoparticles through our fabrication methods. The next. Okay, the next. So that's our goals, the next. So this membrane, just go. Yeah, here. Okay. So our membrane actually is like a staking system. So the first part, we use the chemical reduction method, the signal reduction method. We can control the different function group on the graphene oxide membrane. So they have a different species. And also we know if you use very strong reduction, high temperature, for example, then you can extend the interlayer distance. And now so we want to put some catalyst inside for the hydrogen evolution. That's our dream. Like we want to use in these membranes, the solid membranes, for the energy effects. So depending on the potential, depending on your purpose, we try to convert the electric currents to the hydrogen or oxygen. And then so this kind of material also, I showed you before, it's like a water permeation, and also you can use in the different gas species go through these membranes. Everything happens in our membranes. Can you go to the next one? I think that's the final one. Okay. I think I will stop here. Thank you, Edith. You have patience for me.
Yeah, give applause to Professor Cheng Ho. Okay, and we have the last speaker for this plenary session in the morning. So Professor Markus Diantoro is currently the professor in the Department of Physics, State University of Malang. He is also the vice president of this university, and you are the host of this conference. So the time is up to you for the present. And yeah, he obtained the PhD in the Technical University in
ITB.
Huh?
ITB.
ITB. Okay, ITB, and he will talk about the general rule of the dopant and the magnetic field for the energy application. Okay, time is yours.
Okay, thank you, Pak Edi. Very good morning. Assalamualaikum warahmatullahi wabarakatuh. Thank you, the President of Indonesian Magnetic Society, Pak Agung, the Chairman of the ICMIA, the fourth, Pak Taufik, in the Department of Physics, Pak Sunaryono, and all the colleagues, ladies and gentlemen. Actually, I am not the real presenter as the previous presenters. In Indonesia, it's called pupuk bawang, or maybe the onion kids presenters. Okay, actually my field is, I was working on superconductors material with Pak Agung, Pak Risti, also Bang Togar, and transport to the after superconductors, and then now I am working in the supercapacitors, and previously also superparamagnetic. So at least 3 supers means I am also Superman. Okay, most of the presentation is in red because the material, magnetic materials, magnetic field is actually attracting. It means red is also attracting, like Pulusi headscarf. It's in red. This is my topic: general rules of dopants and magnetic fields on energy conversion. May I take only 5 minutes? And I leave it for discussion, and the presentation is about 50 sheets. So I leave it for the student for the homework. And maybe we have more time for discussion, also coffee break. Next, please. Okay, firstly, I would like, this is just what I would like to share for these 3, and then go to the first, next please. Yeah, I would like to show you what is the importance of the magnetic and magnetic material or magnetism topic in our case. Next, please. Okay. Can you? Unfortunately, it could not seen properly. This is actually the papers of the magnetic and magnetism materials around the world. About 200,000 papers based on Scopus. So you see those three countries on the top one, actually China, USA, also Japan there, South Korea. And we know that those countries also are strong in politics, strong in industry, and also strong in economy. It means it reminds us to the president of the ICMIA and also the president of Indonesian Magnetic Society. If we would like to go to the strong nation, so Indonesia also should be strong in the magnetic industry. because this is also Shin here, that's United States, Japan, China also there, also South Korea. But unfortunately, no Indonesian in the top 10. Next, please. So this is our document in Indonesia. Bang Tokar, can you read it, this one? No, unfortunately. All of top Indonesian university is here, and also all of you are here. This is the topic of the magnetic and magnetism or magnetic materials topic in Indonesia. ITP, ITS, UKM, Universitas Indonesia also here. That's good for us. Next, please. This is special case for Universitas Malang. You see that in the topic of magnetic materials or magnetism at Universitas Malang, this is Pak Taufik, Pak Nandang, Pak Sunadol also there. This is the boss of magnetism in Universitas Malang. Next, please. Okay, these are several examples for researchers who are working on the superparamagnetic or magnetic, magnetism, magnetic materials, and so on. Several are also Pak Naryono, Pak Nandang, Pak Taufik. One of them is mine. Next, please. Yeah, most of Universitas Malang researchers working on these 4 topics. For energy storage and also energy conversion. This is for supercapacitor and battery. And number 2, actually working on the photovoltaic DSSC, also another solar cell types. And biomedical application and drug delivery for Pak Naryono, Pak Taufik, and Pak Nandang. And then also functional materials. So maybe all of the researchers of Universitas Malang also working on this topic. Next, please. Okay, this is my topic. It's just a example for students who are not familiar with the supercapacitors. Supercapacitor actually just capacitors, but we improve the capacitance by reducing the size of the electrodes, and also we separate them with the separators, and also we increase them with the chemical. We know that the capacitor actually physics mechanism, but if you put them together with chemical mechanism, so we have a kind of a supercapacitor. It's increased about 10,000 to 100,000 to 1 million times compared to capacitors, the capacity. Next, please. So we put in the magnetic fields, or if we put also there a composite with magnetic materials, or we exchange with the magnetic oxides, so we can also reproduce or increase with the previous one. Okay, this just a kind of our results. If we put on the just as low as about 50 millitesla, we can enhance the capacitance, not only the power density, but also the energy density. Next, please. Yeah, this is also our previous result. Can go to the next. Yeah, this is just example for some researchers of Universitas Malang working on the how to prepare under magnetic materials, under magnetic fields. So actually we can enhance to align the nanomaterials, or maybe you can enhance the plate to go to the plate likes if you want to. So the 2 dimension of the mechanism, we can get it, and then in turn we can enhance performance. Next. Okay, next, this is just the data of the previous one. Yeah, this, I would like to give this topic to Pak Naryono, Pak Taufik, because this is from Pak Taufik papers. Next. Yeah, same one, Pak Taufik, working on the DDS, drug system. Next. Yeah, you can go further. Next, please. Just example. Yeah, okay. This is a magnetic material for energy storage, battery and also supercapacitors. We can go to the next sheet, please. Yeah, actually this is the magnetic materials as a core of the, what we call it, electrodes. So actually we can use all of the semiconductors for the supercapacitors as well as for the solar cells, as long as they met with the liquid what we use for the electrolyte and so also the separators as well. Okay, next. Okay, I can go next, please. Yeah. Next, please. Yeah, actually, solar cell and the supercapacitor is closely related. As long as you have kind of a semiconductor materials and you can put and modify with some other magnetic materials, dopants and also composite, but for the solar cells, you have to have a kind of transmittance optically. Yep, this is the advantage and disadvantage of the solar cells when we use the magnetic field and also magnetic materials as a dopant or as a composite one. Next, please. Yeah, actually I presented previously. These are some advantages what we need to enhance the electrochemical or performance behavior. We can enhance the redox activity by introducing more oxidation states by using magnetic field or magnetic material as a dopant or as a composite. We can reduce the RCT or transport materials under the ACE measurement. So as the resistance reduce, the conductivity increase. Of course, under the period of the semiconductors, not the conductivity. Okay, next. You can see here, if we use cobalt and copper as also co-dope cobalt and copper together, we can see the supercapacitor performance has increased from 200 and then 300, 400 and then double, about 300 farad per gram. This is the supercapacitor increase higher when we use the co-dope cobalt and copper. Next, please. Yep, this is similar to previous one. We use cerium ferrite oxide and dope with some other materials, magnetic materials, cerium oxide and also nickel oxide and so on. We can go increase with the redox reaction, also pseudo-capacitive behavior, so we can reach out about 1,000 farad per gram at 1 to 0.5 ampere per gram. Next. Okay. This is a similar result. Next, please. Yeah. We can see also similar composite with the nickel ferrite oxide with the PANI. We increase from this also increased with the capacity retention up to 1,000, just remain 9% still presented there. Next. Yeah, these are some result from the randomly taken from the Scopus base. Next, please. Okay, this for solar cell magnetic dope for the energy harvesting or solar cells. Next, please. Yeah, the general mechanism is to manipulate reducing the band gap, also add some more additional band gap and shift to the visible light absorption. So this is just a general rule. So by using that one, we can enhance the photovoltaic performance enhancement. We can also reduce the recombination by applying the magnetic field. If we use a magnetic field, of course it should be magnetic material there. So the transport from the visible light may stay more on the system before exit to the material. So the recombination can be reduced. When the recombination reduced, so the GSC, VOC, and also PC efficiency will increase. Next. Okay. Actually, we can go to the next one. Can you go to the last one? Okay, there's similar results. When we use magnetic materials, magnetic tube, or magnetic composite, or magnetic fields, normally we can enhance as long as the orientation also met with what we need. Next. I think I can go to the last one, number 62. Slide number 62. Next. Similar result we will achieve. Next, you can go to the last one before the conclusion. Yeah, stop. My team also have some presentation in this room. These are some of our group will present at this event on the 4th of ICMIA. Next. Okay. University Malang and Department of Physics and the group of Center of Advanced Material for Renewable Energy, here Pak Nadang, Pak Taufik, also Pak Sunarono with me and other researchers. We are open for a kind of collaboration like co-funding, matching grant with consortium and so on, as long as established with the MOU, MOA, we can fund for this group. These are from our strategic partners. Next, the last one. Okay, I hope we can meet on MRSID meeting on this September at Universitas Negeri Makassar. This year, yeah, not the next year. This year, at the end of this year, we would like to invite you and come and join together. We have more discussion, more broader topic, not only for the magnetism materials. Thank you very much.
Yeah, give applause. Yeah, thank you very much to our three speakers for the very insightful presentation. So we have maybe 15 minutes for the discussion. We open for the Q&A. Any question or comment? Okay. Panitia, mic.
Okay, thank you for attention. I have some question for Professor Cheng Hao Chuang from Taiwan. Yeah. Before I asking about the question, let me to introduce myself. That my name is Milenia Tambunan. I'm from the Sriwijaya University. Okay, I really interesting about your title in the research is add-on ferromagnetic and catalytic nanoparticle to the graphene oxide membranes. So you show about your goals of the research, such as the watering nitration, also add-on catalyst and gas sensor. And for my question is about your opinion of your research. Which of these goals is the easiest to achieve, and which one is the biggest challenge to achieve your goals? Thank you.
Yeah, the simple one is the separation, gas separation, liquid separation. Because the membrane, if we make the thicker, not very not just secret, then it's possible to isolate it, to separate the gas species. But the problem is how can you control the properties, the thickness, to control the water permeations, the rate fast. You can control this one. That's the very minor challenges for the membranes, the separation, the filters, the separation. The hardest one is the catalytic reaction. Because our goal is like we want to have some flake, like paper, you know. Then we want to use this one for the recycling. Even like it's very cheaper, the cost is very low. Then we can use the papers to apply the potential from the solar panel, you know, from outside. Then you can generate the water. You can do the water splitting stuff. And you can generate the water, the gas, the bubble, like hydrogen or water, depending on the metals, the species, depending on the population of the potential. I think that this one is very, very difficult because we want, you know, the goal is over there. So water goes through this membrane. But when we turn on the switch, the potential switch, it will become not only water, but also have some bubble. The gas bubble will go out. It's quite challenging. Not only on the physics, but also for the engineer parts. But I think it's possible right now. Yeah.
Okay. Okay. For the next question.
Okay. Thank you so much. Thank you, so Professor Chuang. I'm sorry, maybe if I wrong to spell your name. Hopefully, it is correct, Professor Chuang.
You can call me any name, Chuang or Chen. Yeah,
it's okay. Yeah. Okay. Let me introduce myself. My name is Yuda Prima. I'm from this university, Universitas Negeri Malang. So basically, I'm really actually get insightful, information from your presentation. It's very nice information. So, by the way, regarding the preparation of the graphene oxide, so you try to prepare the graphene oxide membrane by electrochemical method. So, actually, I'm wondering, can we try to prepare the graphene oxide on a specific substrate using the electrochemical method? Because in your method, you show that you prepare the membrane. I'm not sure whether you get the slurry or something like that. I'm not sure. But here I'm asking whether we are possible or not to prepare the graphene oxide on a specific substrate. Yes. And can I have one very short question? Yeah. And then the second question is about the, the catalytic properties. So you mentioned that when you increase the magnetic field up to 100 millitesla, so you get improved performance of the electrocatalytic reactions. So from my theoretical understanding that when we modify or when we apply the magnetic field on specific magnetic materials, so we can try to tune the band structure near the Fermi level. But we are not sure whether it will increase the density of state in this Fermi level or not. So for example, if we get lower density of state, will we get the decrease, electrocatalytic performance? So I think this is the second question. Thank you so much.
Okay, the first question, can we fabrication the graphene oxide, the membrane on the substrate, right? So we tried using the different substrates like conductivity is the substrate. For example, stainless steel. Second one, we use the gold coating on the silicon. It's very cheaper also. You can gloss the membranes on the gold substrate and stainless steel. I think maybe have some problem for some metals, the substrate, but I don't remember. Some have some corrosion, surface corrosion on the substrates. But it's possible. You can gloss on the substrate. You can gloss the membranes, just the stainless steel, suspending steel is possible. Yeah, it's depend on purpose. The second question is, how can we know the Fermi level tunation, right? Well, I would say it's very hard. The reason you have to use some synchrotron to measure for example, nickel, right? Nickel 3D electron. Then you measure the nickel 3D signal. But they also apply the different external magnetic field, apply the different potential to do the oxygen evolution. But you not only tune the Fermi level, but also the one thing, you have a very strong bonding between the metal 3D and with some substrate. For example, our case is a molybdenum sulfide. Which one is a nickel with the molybdenum or nickel with the sulfur? It depending on bonding. So the bonding means the chemical bonding, like the charge, you have expected to see the charge transfer. You do some chemical bonding or just physical bonding. Physical bonding it cannot work. It has a very strong bonding. It means that you can charge it. You can do the charge transfer from the sulfur, or you can give it a more extra charge inside. And then the Fermi level not only tune the Fermi level, but also you will change the density of state of the whole band structure. So the applied external magnetic field actually will tune the ferromanganic part, and this ferromanganic part also connect to the sulfur, connect to the substrate. Then you will increase a lot of the electrons, the stables on the Fermi level, because in magnetic field outside the external is one. Yeah, so you have to have very strong. The conclusion is very simple. You have a very strong charge transfer bonding between the substrate and the ferromanganic metal. And the second one is you're not only looking for the Fermi level, but also have to see the whole density state with the different species, up or down. Yeah, depending on. Yeah, if you have a very strong one, you have a very, for example, majority spin up is become larger, then you can have more charge transfers, the reactions that happens.
Okay, so maybe there's another question or comment? Student. Okay.
Good morning. My name is Raditya, and I would like to ask a question to Professor Nakamura. So my name is Raditya, and let's say my work is also involving spintronics, and I am interested in your interface designs. I noticed that for the interfaces that you presented, you did not use any, you could say, heavy metal interfaces, right? So since my current thesis is actually related to the Zielinski-Mora interaction, have you previously researched or perhaps planned to research on using probably heavy metal interfaces in the interface designs, or yeah, maybe you plan on using heavy metal, and maybe if you don't, what do you think that DMI can affect the PMA strength of the systems? Thank you.
So yes, my case is, so this time I did use for the heavy metal cases. Because of this one, we have to be switching firstly. So spin-orbit coupling is rather risky because of some kind of, so the damping constant increases. Therefore, we try to using for the more light metals. So, but after second question, look like the second question, the Zielinski-Mora interaction. And this is another very interesting topics. We also now to be calculated for the DMI, and I'm very interested for the DMI property at the interface. So last one, I'm sorry that I couldn't catch for the question on the...
No, that's actually just my question. Yeah, so that's all my questions.
Okay, thank you so much.
Yeah, thank you. Okay, maybe we have another one question or comment? Okay, in the front.
Okay. Thank you. My name is Finan. So my question is to Professor Nakamura. First, thank you for your presentation. And I'm just curious about your interface. You used MgO, magnesium oxide. So for example, if I substitute the magnesium atom with other earth alkaline, like calcium or the others, perhaps it also will have the same pattern, or also I think that we will have like different lattice constant and lattice mismatch. Do you have an insight for like that? Thank you.
First of all, yes, it's fine for the institute, the changing to the like the calcium or something. So importance is oxygen. So the TMR. So the importance is oxygen and ion bonding at the interface. Therefore, your case, the calcium is fine because also the calcium give us stability of the NaCl type structure on the barrier. In a case, it's fine. So however, the MgO is more stable. I mean, very popular. So the experimentalist or some developer don't want to change for this material. But I heard from the colleagues, so they try to change something. So the barrier layer, now to be barrier layer is a key point to some improve for the MTJ. Yes. Thank you.
Okay, thank you.
So how about the alumina?
Alumina is different the crystal structure. Therefore, it's very difficult. So they cannot get for the high TMR. So
few people using the aluminum dioxide. Yeah?
Aluminum oxide, the spinel, in that case is fine. Now the people is working on this kind of because of the spinel, you can tune the lattice constant, implant lattice constant. In that case, indeed, iron and MgO, we have a 4% lattice mismatch. This is the big one. So to reduce for this lattice mismatch, so people working on changing for the barrier layer like the aluminum.
So it's mean until now that everyone using the magnesium oxide. Okay. No question? Okay, the last question. Professor Rizky.
Okay, thank you. Very nice presentation. I have three questions one question for each. First, for Professor Nakamura, it's a general question. How realistic to implement atomic layer insertion in fabrication of STT-MRAM in industrial scale? So the second one is about your opinion. Which one is better to increase the performance of MRAM, decreasing damping or increasing anisotropic PCMA? So this is the question for Professor Nakamura.
Okay, maybe it's okay.
Yeah.
The first.
Yeah. Please.
You guys answer first.
Okay. I'm sorry. The first question is
how realistic to implement the inserting.
They observe in experiment for the perpendicular anisotropy. Also, they try to voltage control magnetic anisotropy experiment. So probably it's possible. Well, my case is a substitution, nitrogen fluorine substitution at the interface. In that case, it's becoming effective. So second question is...
Which one is better, decreasing the damping or increase the PMA? For the MRAM, yeah?
So the colleagues say they want to be more high PMA. But the damping is too low. Low damping is something problem in the experiment. So they want to keep on some suitable number of the alpha. I am not sure exactly, but so the too low is not good for this one, for the switching. Okay. Therefore, I'm sorry, I cannot say, so I have to be asking colleague again. Thank you so much.
Thank you.
Okay.
For the next question.
So, okay, for Professor Chang's.
Cheng Ho.
So it's a very nice presentation about how to increase the performance of the catalytic. You mentioned that the ferromagnetic orientation of iron oxide nanoparticle under external magnetic field can modulate catalytic performance. Could you please clarify the underlying physical mechanism linking the magnetic alignment, magnetic orientation, and enhancement the catalytic performance?
Okay, so the first one is like the nickel monomer sulfide. So I think you're talking about the ion, right? So there will be the second the application, combine the catalytic reaction and the ferromagnetic property. So the second one we are still working on. So in case you want to ask the detail, like a mechanism reaction, I would say right now we already found some ion nanoparticles on the graphene oxide through some very strong oxygen function group. So I should try to looking for this one, the bonding, what kind of oxygen bondings between the ion nanoparticle and our graphene oxide. I would say the defect, the latest property, defect, or vacancy, H, you probably have the most strong reactions because they have extra electron on the side. Then they can give it extra electron to the ion nanoparticle. And I think this one you probably have some the enhancement origin. I would say that, but right now we don't have the experiment for this mechanisms, the calculation of the evaluation. Sorry, I cannot answer the question now, but I think we are trying looking for what's the reasons we can see the enhancement. Because these ones, I think I told my student about the ion oxide nanoparticle and the graphene oxide material. My student, he's interested in carbon dioxide reductions. So it's like a carbon dioxide gas absorption and absorb, right? And I will ask him to do some dissolution because the negative carbon is the propaganda for all the countries to negative carbon to absorb the carbon from the gas or from the water, from the seawater, right, like the ocean. How can you absorb this one? But this one also, we want to also try to some conversion, like to the useful carbon, hydrocarbon, like CO2 reduction, CO2R. But this one, I want to try the carbon, and we want to store this one for some applications. So far, we don't have that. Right now, we are trying to, I think I told my student, try to using this new data, new result. So I asked my student, try to using the different external magnetic field to control orientation of the magnetic nanoparticle with the graphene. So I will say the orientation of staking of this membrane will become different. And we want to control the orientation of the staking membranes. So far we are trying to under this button, but I didn't go to the next one. Okay. Sorry.
Thank you.
Okay,
The last,
yes.
The last one for Professor Marcus. Yes. As we know, we already got announcement for the funding from our government using a BIMA. You know, as far as I know, our group in magnetism got a very small amount of the budget for the research in magnetism, especially supported by our government. Could you please give your comment or strategy to increase the budget for the next year?
It's something political view,
Yeah, actually, this week is a kind of public comments, permintaan pendapat dari government from Risbank for the roadmap of the 2026-2045. I don't know Unpad already got or not yet. But the book 1 and book 2 from print and from Risbank, from Pak Fauzan is already deployed, but this is just the first circular one. If you would like to share your insight, please maybe send your email to Pak Dirjen, because I have seen no magnetic topics on the 8 topics on the roadmap. You should put there. If you don't, please save your magnetic to, let's say, energy, semiconductors, and so on. Because magnetic materials, magnetic field, magnetic materials, and so on can go to all of 8 topics of the roadmap. And this week also, UM leads of the research roadmap of the education this week. And then we send also to complement for the 8 topic of the roadmap. So later we will have 9 topics, not only 8 topics. I suggest you should go, maybe the president of the association, Pak Agung, we can go to Pak Dirjen. So Pak Dirjen is open mind. So we have asked also to put also the education roadmap as well previously. So Pak Dirjen asked to UM to lead the roadmap from 2026 to 2045 to complement on those 8 topics of the roadmap nationally.
Or I need to stop MBG, yeah? Yeah, I need to stop MBG as well. Okay, participants, ladies and gentlemen, maybe we have to go to the coffee break, yeah? So we will finish this session. Give big applause to our 3 speakers. Thank you very much.
Okay, ladies and gentlemen, we will now have a coffee break for approximately 15 minutes. So for keynote speakers, invited speakers, presenters, and participants may collect the coffee break at the south entrance, so the committee will guide you there. Once again, to keynote speakers, invited speakers, presenters, and participants may collect the coffee break at the south entrance, so the committee will guide you there. And for the audience, members who have a coupon, please redeem your coupon at the registration desk located at the front area to receive the coffee break. Jadi untuk yang audiens, silahkan bisa mengambil coffee break dengan menukarkan kupon di meja registrasi depan. And then, additionally, during the coffee break session, there will be a QR code for the online attendance form that will be displayed on screen. And please kindly scan the barcode and complete your attendance before returning to the session. Thank you very much, ladies and gentlemen. Enjoy your coffee break.
The Indonesian Magnetic Society, or IMS, is a professional organization dedicated to advancing magnetism and magnetic materials in Indonesia. Rooted in the historic Magnetic Club conferences from 1999 to 2015, IMS was officially established in 2018 to continue and expand this legacy. Today, IMS serves as a growing hub connecting researchers, engineers, industry professionals, and government institutions. At IMS, we connect, develop, and innovate. We bridge research, innovation, and real-world applications by fostering collaboration across academia, industry, and government. We believe that progress begins with shared ideas and strong partnerships.
Ladies and gentlemen, we will resume the plenary session shortly. We kindly invite all participants to return to their seats respectively. Once again, ladies and gentlemen, we will resume the plenary session shortly. We kindly invite all participants to return to your seat. And please take your seat and prepare for the continuation of today's conference program. We kindly invite once again to our moderator, Prof. Eddie, to come to the stage. Thank you very much for your attention.
Tes. Aman. Aman ya. Okay. Okay, thank you, the audience. Okay, good morning into the afternoon. Okay, this session, we have two presentation, the keynote speaker. First, the Professor Masaki Fujita. Thank you. Welcome to Professor Masaki Fujita. The Professor Masaki Fujita is a Japanese physics specialist in condensed matter physics, and also he's get the doctoral degree physics from Tohoku University. Following PhD, he conduct the extensive research in neutron scattering. In the second presentation, Dr. Mi Jin. Okay, thank you, Miss. Okay, did a South Korea researcher specialist material science, oxide material, spintronic, and low dimension. And now he research focus on the oxide material and oxide spintronic. I think the keynote speaker is very distinguished to this competence. Yeah, now we give the Professor Fujita to get the presentation. Welcome.
Yeah, thank you very much for the kind introduction. Yeah, first of all, I would like to express my gratitude for the organizing committee, especially Professor Nugroho. Okay, he's okay. And also Professor Taufik, for providing me a wonderful opportunity to join this conference, International Conference on Magnetism and its Application 2026. So my name is Masaki Fujita from the Institute for Material Research, Tohoku University, Japan. So today I'm going to talk about the neutron study on spin dynamics in cuprate superconductor and rare earth iron garnet. Okay. So next please. So my research theme are spin-related phenomena and structure-driven functional properties starting with quantum beams. They are my the example. Since time is limited today, I focus on the neutron scattering study on spin dynamics in superconductor and spintronics-related compounds. Next, please. Next, please. Okay. So let me start with the introduction of the cuprate section. So next, please. So this is a phase diagram of prototypical cuprate, so-called this 214 system with a layered perovskite structure. So it's a type of carrier doping into the magnetically ordered motor insulator induces superconductivity. So because of the superconducting phase exists in the intermediate region between the insulating and metallic phases, the spin correlation in superconducting phase have been intensively studied in terms of which view is more appreciable. That is, localized or itinerant picture. For investigating the spin correlation, neutron scattering is very powerful because it can directly measure the dynamical spin susceptibility. However, due to the smallest spin value of 1/2 and the large exchange coupling exceed 100 millivolt in layered cuprate, there is a very weak magnetic signal in a wide energy range. So this feature makes the observation of entire spin excitation in cuprate superconductor difficult. So next, please. So previous works reveals the spin wave excitation in the parent compound, shown in the left side, transformed into an hourglass-shaped excitation upon doping. So this is the dispersion relation for lanthan strontium kappa O4 with several doping levels. So incommensurate low energy excitation directs with doping, while the high energy dispersion is robust against doping. As a result, the waste energy of the hourglass increases with increasing superconducting transition temperature due to the hole doping. Next, please. Yes, okay. So hourglass-shaped excitation were observed in other superconducting cuprate. Thus, the origin of such characteristics must be clarified. Furthermore, so two distinguished properties across the waste energy in the right figure have been reported as a feature of this excitation. That is, the momentum peak width shown in the upper side drastically increases above the waste energy with increased energy transfer. And the local spin susceptibility in the bottom panel shows double peak structure, indicating the existence of two characteristic energy scale of the spin fluctuation. So next, please. So to elucidate the origin of such excitation, the determination of more detailed structure is required. Hence, we carried out high-resolution neutron scattering measurement using a large volume of crystals, shown the left corner, bottom corner, with a large volume of crystals. And the measurements were performed on the chopper spectrometer named Four Seasons, installed at JPAC. Both the SNA ratio and the statistical accuracy were much improved compared to the previous work. So samples used for the experiment were LSCO with a whole concentration of 0.1 and 0.16, which are underdoped and nearly optimal doped superconductors. Okay, so next, please. So now I show the experimental result. There are the constant energy spectra sliced at 4 different energies. Okay, at low temperature, it is difficult to see, but at low temperature, well-defined incremental peak were observed in the low energy side. They vanish or turn into a single broad peak at a high temperature shown by the red circles. However, the signal peaked around 40 millielectron volt remained at even high temperatures. Then high temperature data was subtracted from the low temperature one for the clear visualization of the incremental structure. These are the spectra. Color map shows the subtracted spectra in the energy and momentum spaces. A steeply standing incremental structure becomes clear, as you can see in the figure. Okay, so next, please. So next, we analyze the spectra by assuming the existence of an isotropic peak centered at pi position, and for incremental peak around pi to reproduce the spectra by the superposition of the two components. So they are constant energy slice. They are there, yeah. So it is difficult to show. Okay. So next, please. Yeah. In the fitting process, incommensurability and peak widths were fixed to constant value in the entire energy region because we observe steeply standing rod-like excitation in the subnet spectra. I skip the detail here, but scale factor for each component is only the fitting parameter, very simple. So there are representative fitting result. As a spectra, including a flat top feature, can be well reproduced. The obtained high-quality data allow us to perform the two-component analysis for the first time. There are also the fitting result for the different energy and direction. Okay, so in the right figure. Okay. Red and blue line indicate the individual component, and the purple line shows their sum. I would say the two-component model works well to reproduce the entire spectrum for this x equals 0.10 sample. Okay, so please next, go next. Yeah, and for x equals 0.16 as well. Yeah, next please. Then the local spin susceptibility evaluated for each component plotted as a function of energy. At low temperature, the incremental component is below 40 million volt, and the intensity gradually decreases with increasing energy, while the commensurate components become dominant at high energy. This result implies that superposition of two components with a particular intensity balance form an hourglass-shaped excitation in appearance. In this picture, the reported waste energy corresponds to the energy where the commensurate component becomes dominant with increasing energy transfer. At a high temperature, the incommensurate component disappears, but the commensurate component remains with a comparable intensity to that at low temperature. Next, please. Sorry. Sorry. That is okay. Go back to, yeah, okay. So the right figure, upper right figure shows the temperature dependence of both components measured at 10 million volt. So importantly, the incommensurate component develops below the pseudo gap energy with decreasing the temperature, consistent with theoretical work that shows the appearance of the steeply standing magnetic structure from itinerant electron spin. Therefore, we think the low energy part of excitation is most likely to have the itinerant spin nature. And the incommensurate spectra induced by doping associated with the film surface topology. Okay, so go to the next slide. Yeah. On the other hand, the commensurate components smoothly connected to the high energy spectra, where the ring-like shape spectra were observed in the constant energy slice. The ring widens with increasing energy transfer, quantitatively similar to the spin wave excitation in the parent materials. So furthermore, this excitation is robust against temperature and doping. Thus, the high energy part of excitation would be the remnant of the spin wave, namely the coherent motion of the spin, local spin. Okay, so dancing. Okay. Yes, go to the next slide. Yeah, thank you. So the magnetic excitation have different origin depending on energy transfer, and the existing energy region changes with locking like this. Though energy excitation with an itinerant nature system dependent, and high energy one with local spin nature rather universal, or the cuplet superconducted. That is our picture. Okay, so please go to the next slide. Yeah, next I will discuss the anomalous intensity enhancement in the low energy region. Yeah, next please. So evidence of spin phonon coupling was reported from the internal intensity enhancement of spin excitation at the energy where the optical phonon branch intersect. According to our picture, the intensity of the low, this energy region is predominantly associated with the itinerant component. Yeah, next please. So to clarify the origin of our intensity enhancement with checking the consistency of our picture, we performed a comprehensive study on several samples, including parent compound, that is X equals 0, and superconducting and metallic LSO, and isostructural insulating nickelate oxides as the reference. So measured concentration and temperature are summarized here in this phase diagram. The right figure shows the spin excitation and phonons. At low temperature, the intensity enhancement can be seen in the superconducting sample, where the optical branch intersect. On the other hand, no clear enhancement was observed in the insulating and metallic samples. In particular, the non-superconducting metallic sample show no magnetic signal, and only the optical phonon exists. This indicates that the phonon solely does not show intensity enhancement that suggests the interplay between spin and lattice dynamics, more complex dancing with phonon. Okay. Yeah, next please. So there are the constant energy spectra for several samples. The peak correspond to the magnetic signal. Then we extract the magnetic intensity by subtracting phonon background as evaluated the local spin susceptibility. Yeah. The results are plotted in the right figure. This here as a function of energy. The peak structure is presented in the superconducting sample, but absent in the insulator. So next we investigated the intensity in the colored region shown in the right figures to see how intensity enhancement behaves with doping. So next, please. Yeah, there's a sorry. Yeah, doping. Okay, so as a result, a dome-like feature was clarified that this behavior can be interpreted as that intensity increase in the underlocked region with increasing the intensity of carrier and decreasing the overdoped region with weakening of magnetic correlation. Thus, intensity enhancement could have originated from the interplay among spin fluctuation, phonons, and mobile carriers. We calculate the phonon mode for the parent compound based on the shell model shown in the right figure. There are several modes at a particular energy and momentum position where the enhancement was observed. Among them, it's difficult to see. But yeah, there are three different modes. Among them, the phonon mode are associated with the out-of-plane motion of kappa and oxygen atoms, which produce the potential for trapping one-dimensional charge alignment, and hence could be coupled with the metallic charge stripes. The dynamical nesting condition modifies the phonon may affect magnetic intensity. Okay, so please go to the next slide. Here is a summary so far. We studied spin excitation of Q-press superconductor with neutron. Our results indicate the hierarchical energy structure of spin excitation, showing localized and itinerant spin natures. The intensity enhancement was confirmed for the superconducting sample, which suggests an interplay among spin lattice and charge dynamics, degree of freedom. Okay, so please go to the next slide. Yeah, now I move on to the spintronics related compound. Please go next. Yeah, so spin current in the is a flow of angular momentum in material, and it's attractive attention to control various physical properties. Since magnon can carry the spin current in insulator, it is important to study the spin dynamics. Here are the crystal structure and the magnetic structure of yttrium ion garnet, which is a well-known ferrimagnet used as an insulating part of spin Zeebeck's effect device. Next, please. The ferrimagnet has a degenerated magnon mode. Yes, shown here, but difficult to see. With opposite polarization, namely the direction of precession. So these are typical acoustic and optical mode carrying spin current oppositely in direction. Recently, the temperature dependence of magnetic excitation were calculated theoretically, shown in the bottom figures. In this figure, red and blue color represents the magnon with opposite polarization. So at low temperature, only the acoustic mode is thermally occupied and generates spin current. However, at room temperature and above, due to the thermal population and softening of the optical mode, this mode can also contribute to the spin current. Since the polarization of the two modes is opposite, the spin Zeebeck effect signal, SSC signal, decreases at high magnetic information separately by selecting the up and down spin of initial and scattered neutron. So these are the unpolarized spectra. So we can see both acoustic and optical mode. And for our polarized neutrons experiment shown in the right bottom figure, confirms that the signal is of magnetic in origin. So furthermore, it was clarified that these modes have the opposite sign, as shown in the different colors, which is consistent with the calculation. Thus, polarization is an important factor for the spin current. Okay, next, please. Yeah. Building on our success in observing the behavior of yttrium ion garnet, we turn our attention to the magnon of terbium ion garnet. Unlike YIG, yttrium ion garnet, terbium ion garnet exhibit a unique behavior in sign reversal of SSS signal shown in that figure. So is this intriguing behavior not observed in YIG result from the presence or absence of rare earth moment and their interaction with iron moments. The magnetic compensation temperature, where the total moment becomes zero, is a key factor in this unique behavior. So our polarization spectra shows that with increasing temperature, both high energy and low energy mode softens, as shown in the middle figure of the bottom one. And the energy gap of the low energy mode closes at the compensation temperature. Okay. So regarding polarization, shown in the bottom right figure, opposite sign for the two modes were confirmed. Moreover, marginal polarization of the two energy modes at low temperature is opposite to that at high temperature, indicating the spin sign change on crossing the compensation temperature. Thus, the sign reversal in the SSA signal is associated with the change in the marginal polarization. And the spin current in terbium iron garnet is governed by the mode softening and sign change of polarization. Okay, so next please. Yeah, in conclusion of this part, we observe the marginal excitation and their polarization in iron garnet and clarify that the thermal evolution of marginal mode and compensation of polarization contribute to the spin current. Yeah, next please. Okay, so let me summarize my talk. Yeah, we studied spin-related phenomena and structure-driven functional property. And I introduced a couple of topics today, although I didn't touch them today. But we have crystal growth device and neutron scattering devices. And we are making the most of these advantages in our research. In the future, we plan to focus on using polarized neutron more effectively with a new device. We are developing it now. So at the same time, we use quantum beam in more complementary and such issues, not only neutron but also mu and synchrotron X-ray. So I would like to make some collaboration, new collaboration with you. Thank you very much for your attention.
Okay, thank you, Professor Fujita. Insightful the presentation. Okay, we get the applause to Professor Fujita. And next, Professor Dr. Mi Jinjin to about the
Hello, nice to meet you. My name is Mi Jin. I'm from South Korea. Today, I'm working at the Institute for Basic Science. So today, I'm going to talk about tunable spin and charge transport at functional materials system. This is just a titled one. So before talk about it, I would like to introduce about my institute. Next, please. So my institute is actually established in 2011, November, and it is motivated from Max Planck Institute, and it is goal for accelerate transformation through new knowledge, ensure excellence in research, and stimulate collaboration without boundaries. So because it is motivated from Max Planck Institute, next please. It has seven research institutes and 31 research centers. Next, please. Yeah, and next, please. 2 times more. Yeah, next, please. Yeah, as you can see here, all around the country, there is several research centers and institutes are originated there. And next, please. Next. Yeah, I am working at Ulsan City, which is originated at UNIST, which is the co-university and institute. And then, next please. Yeah, and my director of my center is Prof. Rodri Ruop, who is really famous for graphene oxide material and graphene material and so on. And from next September, I will move to another center. Next, please. Yeah. Next, please. Yeah, another center, which is located at Pohang City and in the Postgraduate, which is also another famous university, co-university and institute. Next, please. And here we have 3 centers in the Postgraduate. So you can see there at that building, there is a Center for van der Waals quantum solids and geometry and physics, and Center for artificial low-dimensional electronics system. So if you are interested in, you can searching for that homepage. Next, please. And our center, my next position, our center director is Professor Moon Oh-jo, and including Moon Oh-jo, there is several professional professors and researchers that exist, including architecture growth, microscopy, and spectroscopy, and so on. So already they are studying so much higher level research related with van der Waals heterostructure. And as you can see there, there's several representative papers are reported. Next, please. And their professionalism, one of the specialists is the amazing equipment system. As you can see there, they have in-situ processing equipment system. Next, please. Yeah, at the first 5 line, they have a molecular van der Waals structure growth system. So each of equipment position, they can grow different van der Waals material. And then, next please. And then, after then, they don't have to take it out the sample, and they can directly move the sample to the characterization system, including microscopy, and also they have several specialized spectroscopy system as well. So that is one of the strong points for that research center. So if you are interested in, next please. I am hiring 3 or 4 doctoral researchers and postdocs. So if you are interested in, please contact me. And next please. So now I would like to introduce about my research about oxide, full oxide-based structured spin-to-charge conversion and spin-orbital-induced magnetization switching. That is the charge-to-spin conversion. So next, please. So as you know, I will briefly introduce about spintronics. So the electronics is just using the electron flow or electron movement. But next, please. Next. Next. Yeah, next. Yeah, as you know, the spintronics is using not only electron flow, but also spin degree of freedom as well. So spin density is really different with the electron density, as you know. Next, please. Next. So most of the unique thing you can use for the spintronics is the spin-orbit coupling. So there is 2 types of spin-orbit coupling mechanism. One is the intrinsic spin-orbit coupling, which is effective field due to periodic potential, and the other one is extrinsic spin-orbit coupling, which is effective field due to non-periodic potential. That is because of the impurity, vacancy, and so on. So the intrinsic spin-orbit coupling is comes from bulk or interfacial structural inversion symmetry breaking, and extrinsic spin-orbit coupling, that is because of the impurity or vacancy and so on. There is 2 or 3 kinds of scattering mechanism. One is a scattering, the other one is a side stump scattering. So next, please. Next. So if you use that kind of intrinsic, or if you use that kind of intrinsic or extrinsic spin-orbit mechanism, then you can experimentally observe Rashba-Edelstein effect, which is the interfacial spin-orbit coupling originated effect, and the other one is a spin-hole effect. So you can see here at Rashba-type Edelstein effect. Next, please. Yeah, when there is Rashba type spin splitting exists, and if you apply current through the interface, then at the moment the current induced spin accumulation can be happen. And next, please. Next. Next. Yeah. So if you want to measure this Rashba-Edelstein effect, then you can use the inverse Lashiba-Edelstein effect. As you can see there, at the moment of the spin accumulation, then if you add the high-spin orbit coupling material or interface, then you can obtain the spin-induced charge accumulation at the edge of the line of the sample. Next, please. And spin-Hall effect, maybe you guys already know about that. Spin-Hall effect can be happen not only bulk material or interface as well. So spin-Hall effect is can be happen at the high spin orbit coupling material. So charge current can convert to spin current is the spin-Hall effect, and the other version is the inverse spin-Hall effect. So mostly I am using this kind of two types of effect, Lashiba type spin orbit coupling or spin-Hall effect. So next, please. So at this first presentation is research is the spin to charge conversion at magnetic oxide and push it to the conductive oxide interface at the full oxide structures. Next, please. So without using ferromagnetic material, you can study this kind of a spin-Hall effect induced pure spin current by using geometric effect or Lashiba type spin splitting or Lashiba type spin orbit coupling. You can measure this kind of non-reciprocal charge transport at this push to the oxide interface. This is what I have done from 2017 to 2019, and then I move on to next, please. I move on to using the oxide ferromagnetic material. So before I use oxide ferromagnetic material, if you want to use ferromagnetic material, they use the ferromagnetic metallic material. As you can see here, you can use the spin injection method or spin pumping method by using ferromagnetic resonance. So between two, I start to use this ferromagnetic resonance method by using oxide ferromagnetic material. Next, please. Yeah, so first of all, to use the ferromagnetic oxide material, I did set up the cryogenic ferromagnetic resonance system as an option of PPMS. Maybe you guys know about the PPMS. This is the cryogenic system to measure 2 Kelvin to 390 Kelvin temperature range, and it can measure magnetic field up to 8 Tesla. And if you do want to measure the ferromagnetic resonance system as an option, you can use a microwave signal generator. Then in my case, I used up to 20 gigahertz microwave signal. And you can see at the diagram, you can put the sample in there, and also you can make some waveguide for signal generator, and also locking amplifier can measure the ferromagnetic resonance signal, and nanovoltmeter that can measure the spin to charge conversion. Next, please. So at this diagram, if you do make this quasi to the STO interface, and upper side, if there is the ferromagnetic oxide material, and with microwave signal at the upper side, you can imagine that ferromagnetic resonance can be happen, and then at the same time, the ferromagnetic resonance can affect to the oxide interface. Then the oxide interface has a spin-orbit coupling enough to measure, then you can obtain the red color spin to charge conversion detection, which is the spin pumping. Then that is itself can be evidence of the spin orbit coupling at the interface. Next, please. So I made oxide-based fabrication condition and with 2 types of plasma treatment and annealing process. And after first plasma treatment, you can deposit magnetic oxide material. Next, please. And as you can see here, I first choose ferromagnetic material as LCMO material, and as you can see, if you make the quasi 2D surface and then LCMO material is deposited, even though the surface morphology is different, the X-ray diffraction plot shows the epitaxial relation, and it has a similar lattice constant as well. Next, please. And the LCMO, deposited LCMO property is also showing great reasonable property, and the XLR measurement can show the LCMO thickness around 15 nanometers, and its magnetic property shows that behavior, and it shows maximum magnetic moment at low temperature. That's why I need the cryogenic FMR system. And for the Cauchy to the STO interface, you can measure the interfacial contact method, and then you can see temperature dependent resistance shows metallic behavior, and LCMO's temperature dependent resistance shows the semiconductor to insulator behavior. So you can separately divide the contact resistance, the material signal from LCMO or Cauchy to the. Next, please. So this is the main data of the LCMO layer. So as you can see here, the ferromagnetic resonance is coming gradually from 5 gigahertz to 15 gigahertz. And by using that FMR signal with that Lorentzian function, you can obtain the resonance field dependence frequency and frequency dependence delta H. From that plot, you can extract the characteristic value of the gyromagnetic ratio, effective magnetization, and Gilbert damping constant, and so on, by using that Kittel's equation with that graph and the Gilbert damping model with that graph. So next, please. And then, as you can see in this page, at the same time of A and C of ferromagnetic resonance signal, if you do contact the interface and you can measure the nanovoltmeter signal, then you can obtain the spin pumping signal, as you can see, B and D plot. So B and D plot shows the clear spin pumping signal depends on temperature, and as well depends on external magnetic field. And next, please. So at 5 Kelvin as well, you can obtain the spin pumping signal. So it depends on temperature from 510 to 510. Then you can see the spin pumping signal is gradually decreased. And from those characteristic value of LCMO and spin pumping signal as well, you can calculate the effective spin mixing conductance using that equation and spin density using that equation. So from those calculations, you can calculate the characteristic inverse Lashba-Edelstein effect at the interface. That is the spin to charge conversion efficiency, which is the 2.32 nanometers. So that is clear evidence of interfacial of spin-orbit coupling exists, and it is strong enough value as well. Next, please. So from this result, we published one papers, and also this is collaborated with Professor Jason Robinson from Cambridge University. I did PhD at Cambridge University, so I still work with him. And next, please. Next one is using same material structure but inverted, opposite version. The previous one is ferromagnetic material is resonanced, and then the spin signal is effective to the interface. But this one is, if you do apply current to the interface, then that interface can have high spin orbit coupling, then it can make orbit talk to the ferromagnetic material. So next, please. Yeah, that kind of study at full oxide structure has been firstly reported at 2019 by using strontium iridium oxide as high spin orbit coupling material and strontium lutetium oxide as ferromagnetic material. Next, please. And I want to study about strontium titanium oxide surface. So in this paper, they only measure the spin orbit torque is possible, and it is strong enough at the strontium oxide surface itself, and they didn't obtain magnetization switching. So next, please. So I use the same material structure and STO and interface, conducting interface, and ferromagnetic oxide. I used the LCMO material as well. Next, please. Next. And so making my device fabrication process is the same. And as you can see there, I made a simple hole bar geometry device, and XLD property is similar. And depends by measuring the different direction of MPMS, I mean magnetic moment measurement of the LCMO pattern, the LCMO materials magnetic moment shows that the magnetic LCMO has tilted EG-axis magnetic property. Next, please. And with considering about that, and also this one is Cauchy 2D STO's property. Next, please. And with considering that one, you can also imagine this magnetization switching behavior well. So BC graph shows magnetic field dependence, planar hole resistance behavior. As you can see there, even though this planar hole resistance behavior is detected from interface, not LCMO material. So you can see there, if you apply external magnetic field, I mean sweep external magnetic field, and if you measure the planar hole resistance behavior, then you can see clear magnetization switching behavior. It means hysteresis is coming, and at opposite current value as well, it is more important. You can see that between -1 milliampere to -2 milliampere, it shows clear magnetization direction from clockwise to anti-clockwise is showing. So that is the clear evidence of the magnetization switching. And furthermore, that the graph DEF shows the strong improvement of the magnetization switching. As you can see there, I applied the pulsed current to the interface and then measure the hole resistance. You can see at -0.1 Tesla to 0 Tesla and plus 0.1 Tesla, there is clear magnetization switching related signal is coming. I mean, hysteresis curve is coming. And as well, -0.1 Tesla shows anti-clockwise, and plus 0.1 Tesla shows clockwise. So it is a tunable magnetization switching. And as well, at 0.2, you can see the magnetization switching data is coming. That means the field-free magnetization switching behavior is observed. So next, please. So for that one, I did the system, after that main data, I did the systematic analysis, depends on external magnetic field from 100 millitesla to -100 millitesla. You can see that there is clockwise switching behavior to anti-clockwise switching behavior as well. And if you do make this guideline, that guideline matches the LCM's cohesivity field. So it is really reasonable data. And also at zero field, you can see that field-free switching behavior depends on initial external magnetic field as well. So we did analyze about that, and also LCMO has pretty thick, 15 nanometers thickness they have. So we think about the mechanism of the magnetization switching shame can be happen not just the one magnetic domain is flipping like that. It is effectively, gradually increasing from the magnetization switching behavior. So that is the mechanism discussion under that figure shows. Next, please. So from this study, we summarized about this. This is the field-free magnetization switching of LCMO enabled by interfacial spin-orbit coupling at all oxide full structures. Next, please. So this is nowadays second under revision at materials today. So up to now is my talk. Or can you move on to next 2 pages? Oh, just the previous, yeah. Yeah, this is my research overall. So I am mainly focused on oxide-based spintronics, but I am expanding the other researches as well. As you can see there, I'm doing charge transport study, which is quantum diffusive transport behavior at specific TMD material and process engineered material. And also I have some collaboration research related with defect engineering and ferromagnetic resonance study and study related things as well. Next one. Yeah, this is my collaborators. And next one, please. Yeah, thank you. This is my, yeah. Thank you so much.
Thank you, Dr. Jin, the nice presentation. The two presentations about the spin and conversion, we have some Professor Fujita about the magnon, and the Professor Jin about the some exploration the FMR in the high field. So in this session, we get the question for the keynote speaker. You can hands up the hand. Okay, we get the maybe three questions. Okay, please. Okay, yeah. One. Okay. Another. Okay. Two. Yeah. Okay. Please, please Diana, maybe. Okay. Yeah. Okay. Okay. 1, 2, 3. Okay. Yeah. Okay. Okay. Yeah. Okay. Yeah. Please. Yeah. Okay. Yeah. Okay. Baik. Sorry. Ada satu. Oke, makasih.
Tes.
I would like to ask a question to Dr. Mijin. I might miss your explanation, but can you explain what is spin to charge conversion and how did you did that?
Spin to charge conversion is a spin signal can be detected to the charge conversion. So which means at my first study, I did ferromagnetic resonance I did make ferromagnetic resonance on the ferromagnetic material, and that resonance can give the spin signal to the interface. Then the spin interface can have upper spin or lower down spin majority electron. So that electron can move this side more and this side less. That can make voltage differences. So that is the spin from magnetic material to charge to the interfacial material conversion. Yeah, that is the spin to charge conversion. Is it understandable?
It is understandable.
Yeah.
Thank you so much.
Okay, thank you very much for the time and it's very good talk. My name is Rizwan. I am from the BRIN Research Center of Indonesia, and actually I'm not too familiar with the topic, but I think the result is very interesting. I see that there is the correlation between the VMR resonance, ferromagnetic resonance, with the frequency for the structural sample of the LCMO, quasi 2D STO and STO substrate. And I saw that when we try to improve the frequency and then the magnetic external shifting to high, correct? My question is that why when we try to improve the frequency and then the magnetic external become improved? And the second is that how about when we try to extend the structure of the sample? For example, the ferromagnetic with the paramagnetic, is there any coupling, magnetic coupling that is, and then causing the different spectrum of the VMR resonance? Okay, thank you very much. To Dr. Mi Jinji. I'm sorry.
Nice to meet you, by the way. Actually, first question I couldn't understand well. What was that question? I will answer second question first.
Okay, when we try to increase the frequency, and then
Frequency.
I saw the spectrum between the PMR frequency
Yeah.
for the y-axis and the x-axis is magnetic external. It's become shifting, correct?
Yeah, right,
Shifting.
right, right.
I want to know why when we try to improve the frequency and then shifting to the B external.
Yeah, it depends on material property, character, material to material as well. In my LCMO sample, it depends on what should I say, thickness as well. So if you, in my case, I varied from 1 to 20 gigahertz. So it shows a clear microwave signal. I mean, ferromagnetic resonance signal from 5 to 15. So it depends on some of the frequency region, some of the sample cannot show. So it has some dependency of the material. Yeah. So if you can increase more, then the shift will be happen as well. But it is not shift all the way. It can go back as well sometimes. Yeah. But the origin of that one you can, I think I'm in experimental physics, so you can ask to the theoretical physics. Yeah. And the next question was structure, I mean, ferromagnetic material change is possible. Ferrimagnetic material change is clearly possible, but paramagnetic, if there is no hysteresis gap, I mean coercivity, then resonance can be happen, but it is hard to detectable, and also spin to charge conversion is, I don't know, I didn't try it, yeah. But ferrimagnetic or antiferro is, some of the papers are already, I think, approach it, and they show some result. Yeah.
I mean, when we try to combine between ferromagnetic and paramagnetic.
Yeah, that could be possible as well, and it's also some competitive relationship, so that kind of research could be interesting as well, yes, yes.
Okay, thank you.
Okay, Professor Fujita and Dr. Jin, it's a very nice talk. I have one question to Professor Fujita. It's a very interesting data for superconductivity. So you said that there is anomalies enhanced in spin excitation. It is occurred especially in the point between optical phonon and magnetic excitation, and it only appear in superconductivity. Do you think this phenomena consider direct evidence for spin phonon coupling rather than spin fluctuation alone?
No, it's a coupling between among spin fluctuation and lattice times and charge mobility. Yeah, that is, I mean, the very complex phenomena. And as you said, that kind of phenomena can be seen in the only superconducting sample. Yeah, not in the insulating sample. For example, the ratio with the concentration less than 0.05, that is insulating phase. We cannot see any evidence. So yeah, only. And also the overdose sample, metallic phase. Metallic phase is not a superconducting phase. We cannot see spin fluctuation. Yeah, no enhancement. Yeah.
Okay, okay. So it's very complicated.
Yes, very complicated.
Okay,
Yeah,
okay.
so.
Okay, thank you very much. Yeah. Mau tambah? Yeah.
Just in connection to that, can you comment on the charge density wave?
Yeah, that is very interesting point, but we didn't see any relation with charge density wave. Yeah, maybe next time.
Okay, thank you. Another question for Dr. Jin, it's okay? Dr. James, your study combines a lot of parameters, a lot of characterization, such as a spin hole transport. Then you compare with Hasley precision spin orbital torque measurement in oxide interface. How universal are these phenomena across different oxide
heterostructure. And then the second one, what make STO, strontium titanium oxide, based system particularly advantage compared with some established spintronic, such as heavy metal or topological insulator? Thank you.
Sorry, I couldn't understand. First question.
The first question, yeah, there are two questions.
Yeah.
First question is how universal are these phenomena across the different oxide heterostructure?
Even oxide what?
Oxide heterostructure material. Yeah.
So, do you asking me about choice?
Yeah,
Or,
yeah, about comparison with other oxide.
To be honest, I used to, from my PhD course, I used to study about strontium titanium oxide material. So that's why still I am studying about strontium titanium oxide. But upper side, the ferromagnetic material, that one I have several choices such as LCMO and PCMO and SRO and so on. So the first choice was because of I deposit and I learned to PLD deposition. At the first time I used that material. That was just first choice, but I am now have that kind of 4 different samples that has 4 different coercivity and magnetic property and so on. So I have nowadays comparing that property. So maybe I will in the near future I will publish about that one. So that kind of publishment is coming out. Maybe you can see that paper. And the second question is, you mean STO heavy metal, STO interface?
Yeah, comparison, the advantage of strontium titanium oxide compared with the other established spintronic, such as heavy metals, for example.
It has some advantage. Strontium titanium has some advantage. So such kind of, if you do apply argon plasma treatment on the surface, you can easily make conductive surface. And you can control the thickness as well, the conductive thickness. So I did hardly control the thickness less than 5 nanometer to make interface. So from the XLR measurement, I defined that conductive interface is less than 5 nanometers. So that can make, I can believe some more about that is originated from interfacial effect. If there is thickness is higher than the spin hole effect through the vertical direction and interfacial direction can be happen together, right? So that's why I choose strontium titanium oxide. Is that answer?
Yeah, okay. Thank you.
Okay, the other question? Okay. Maybe the last, yeah? Okay. Okay, yeah, okay, no problem. Okay, this is
okay. Thank you. My name is Finan, and I want to ask a question to Dr. Mijin about.
You guys like me so much.
Okay. So in your presentation, you used LCMO with interface with the STO, and you say that there are like ferromagnetic resonance at the interface, right? So I just want to ask that, first I want to make sure that you only consider like one certain concentration of CA from all of the possible concentration of LCMO, or I want to make sure first.
What concentration? CA is
Yeah.
concentration.
Yeah, CA is concentration.
Yeah, sure. Yeah, we use target material for PLD. We use a 7:3 ratio between LA and CA. So that target material can make that kind of semiconductor behavior and also some semiconductor to what is that, insulator transition with lowering the temperature. Yeah. So I believe that ratio cannot change too much if you deposit using PLD. But yeah, but there could be some deviation can be happen, but in between CA component, the in between 0.3 to 0.5 can make the ferromagnetic material, but if it is larger than or less than, it can change the material property from not ferromagnetic, and also some structural change could be happen as well. Yeah, I know, but I believe that is the inner that ratio. Yeah.
Honestly, I want to ask about is that, for example, I use different concentration. I imagine that, so I have different lattice constant like that from the crystal. So does the lattice mismatch between the two layers also determines that?
Yeah, can be effective as well. Yeah, right. You're right. Yeah, so because I did plasma treatment on the STO surface, so you can imagine that STO surface, even though as a starting it was a TiO2 terminated surface, but I did the plasma treatment, so it has so many defects. So after deposit the LCMO material, even though LCMO is thinner, almost epitaxial relation and single crystal-like structure, from the XRD analysis, you can imagine that there could be so many defects can be happen. And in between that, I didn't put at this presentation, but dead layer is also exist at the LCMO layer, so around the 5 nanometers, something like that. So spin cannot directly go, electron cannot directly go to there. It is effective to the surface, not going electron. Yeah, it's mean, yeah.
Thank you, Doctor.
Okay, Adin? Yeah, okay, maybe the last, yeah? Okay, maybe. Okay, please.
Okay, thank you very much for this opportunity. First, thank for the presenter for nice presentation. So I have a question for Professor Michin. Yes, regarding with the oxide interface. So in my experience, in the oxide interface, there are emergence of the two-dimensional electron gas system. And in that case, unfortunately, the spin-orbit coupling is very small. So do you have any comment how this small spin-orbit coupling can induce such as spin-orbit torque or spin-to-charge conventions?
Yeah, great question. Yeah, I did plasma treatment on the surface can make not only conductive enhancement, but also it can enhance the extrinsic spin-orbit coupling as well. So actually, I was really worried about there could be combined the spin Hall effect and as well Lashiba type spin orbit coupling. I mean interfacial spin orbit coupling and spin Hall effect with that transverse could be happen as well. So I measured several times to define which one is majority. So I didn't put here, but if I measure some, anyway, first answer is spin orbit coupling is enhanced from the treatment and structural, or should I say, the strain can make that kind of thing as well. But to distinguish about that one, spin Hall effect and Lashiba type spin, Lashiba-Edelstein effect, I did measure 2 omega resistance several times. So it shows a strong Lashiba spin orbit coupling existence related behavior was shown. So I decide that this is mainly, even though there is a small spin Hall effect can be happen as well, but it is thinner enough if and particular transverse, I mean G-axis spin Hall effect can be minimized because the interfacial thickness is small, and also from the 2 omega resistance measurement from Rakin amplifier, it shows the clear Rashba-Edelstein effect related signal is coming, which is the non-reciprocal charge transport actually. So I believe that interfacial SOC is dominant. Yeah, like that.
Okay, we give applause to the keynote speaker. Okay, again, we thank you for the nice presentation, and thank you very much. I think this the one I think this research about the SOC, SOT in the spin to charge conversion is very important to spintronic device. Thank you very much again. Okay. Okay.
All right, ladies and gentlemen, we will now have a break for lunch. So to keynote speakers, invited speakers, presenters, and participants, you may take your lunch in the south entrance, just like the coffee break. Once again, for the keynote speakers, invited speakers, presenters, and participants, you may take your lunch in the south entrance. And then for the audience members who have a coupon, please redeem your coupon at the registration desk located at the front area. And later, we will continue for the plenary session. And please, ladies and gentlemen, have a good lunch. Thank you.